Good morning, everyone, and welcome to our live ATS webcast seminar, Acoustic and Sound Control Design Solutions. I'm Fulgence and I'm your moderator. I'm also accompanied by our team who will support us throughout the event. We have 3 courses for you today, and it's my job to let you know exactly where we are throughout the day. You'll see me pop up after each speaker and make sure our speakers start and stop on time. And if you're having any technical difficulties, try logging out and then back in, and that normally resolves most technical glitches. But if it doesn't resolve it, please let me know in the Q&A. And if you happen to be in a conference room watching with a colleague or at home watching with a partner, please check to make sure that you are each logged on with your assigned Zoom webinar link. That link is attached to your ATS account, which is how we report credit on your behalf. So if you're not already, please take some time now to log into a separate device or a second window so we can make sure that you get the credits you deserve. Please also note that we'll launch poll questions during every presentation, and we ask that you participate in those polls so we can confirm your attendance. Let's go over a few quick housekeeping notes to help you get the most out of today's session. Please use only the Q&A for all questions, including help with session codes or anything else, and anything you'd like our speakers to address. Please do not submit questions in the general chat. They will be lost there, so please use the Q&A, and also we can add that to the Q&A report. And also, we kindly ask that you do not post any questions anonymously. If you post questions anonymously, we are unable to verify your attendance for credit purposes when questions come in without a name attached. And also, please note that this broadcast is also live on YouTube in 4K. If you would like to join, the link is there in the chat for you. But please have access, keep access to this Zoom webinar so you can participate in the polls and in the Q&A. So please remain in the Zoom webinar to have access to all those features. But if you would like to view this in 4K on YouTube, go ahead. The link is there in the chat for you all. Today's seminar features 3 AIA HSW, 2 GBCI, 3 AIBD Primary, and is valid for the following Canadian provinces. We will report AIA, GBCI, and AIBC credits on your behalf within 10 business days. And if you're a member of AIA, GBCI, or AIBC, please check to make sure that your association numbers in your ATS account are accurate so we can ensure a smooth crediting process. And for everything else, you'll get a certificate in PDF form. That is 1 certificate for every course you take with us today. And those will be available immediately after entering your session code. And if any of you are new to the session code process, I'm going to review that after our first course is done. And where can you find those certificates? Once you log into your ATS account, you'll click certificates on the left. Then you'll see all the courses you've taken here at ATS. And to the right of that, you'll see a small certificate icon. When you click that, your certificate will pop up, and this is what your certificate will look like in PDF format. And handouts from today's speakers are also available for download from your ATS account dashboard at atsseminar.com. And once again, if you're new to this, I'll explain how to access your dashboard after the first presentation, which is polyethylene, sustainable plastic for exterior acoustics by Spencer Kelly with Old Castle. Spencer, hello.
Hey, hello. Hello, can you hear me?
I can hear you.
I'll leave my picture off the screen because I always get a bad signal.
No worries.
And my camera doesn't work good anyways. So
okay, no worries.
Sometimes I disappear, but let me share my screen here for you.
Absolutely.
Okay. Then share. All right, can you guys all see it?
I'm just waiting for it to go full screen on our end here. Yes, it is all set. Take it away.
Okay, so I would like to thank everyone for attending. My name is Spencer Kelly. I work for a company called Old Castle, which seems to be a name a lot of people know. A couple things just to clear up at the beginning before the presentation. Polyethylene, we make a polyethylene fence, and it is a patented product. We've spoken with the AIA, and because we are the only people who make this, at times during the presentation, they've given us the okay to maybe mention our product. No one else makes a polyethylene fence or sound wall. And that's something we're getting into more and more as the years go on. But I'll explain where all that came from. Number two, this presentation is not the presentation we will continue on with next year. We're working to create a much more technical and detailed acoustic presentation. So if you come back next year and you see a similar title or one from us, it will be a different presentation. Part of the reason for that is as we became more involved in sound and acoustics, it was kind of an unexpected thing. We created a presentation, but now that we're heavily getting into it, we're working more with, DOTs and rail, transportation departments and cities where things are much more technical and they need more testing in this. We are redoing the entire presentation. So this presentation here is a very simple overview of acoustics, some of the test methods, things like that. But it's very basic. So if you have any understanding about acoustics, this one should not be too complicated. It may be dumbed down too much for some of you that do understand acoustics. So, like I said, if you'd like a much more technical one next year, we will have that available. So, to begin, we are Oldcastle. Most people know that name, Oldcastle. I am the national architect, engineering, and national account manager. So, I live in Denver. I cover the entire country. As I said, a lot of this will be basic stuff, so I may skip through some slides because it may not relate a whole lot to architects and specifiers. Some of this is intended for general contractors or maybe owners, people like that. But we will describe the functions and benefits of polyethylene, how it's manufactured because it's different than vinyl, some of the chemical attributes. We'll talk about acoustics, of course, some of the test methods that are used, positives and negatives to that, and I'll explain why that is, and then some of the environmental and health aspects of the product. So you know this, a lot of this is basic stuff. We started out manufacturing fence, and it was residential. We make the product in Orem, Utah. So you'll notice the product has kind of a southwestern look sometimes. A lot of the pictures do, but we make it in different styles, which I'll show at the end. So that is how this started. And then we noticed it had an acoustic property to it. And again, that's how we started getting into this. My background is, and how I got into acoustics, because it seems like there's not a lot of people who are on the manufacturing side of things that have an acoustic background. I worked for a company, Axel Nobel, that the Nobel Peace Prize people, even though I had nothing to do with that. It was in their plastics division, and we did interior acoustics between floors. So if any of you have seen that Johnny Depp divorce, where they were fighting over his penthouse in Los Angeles, I did the acoustics on the interior there. Now that was interior acoustics, and a lot of the test methods are intended for that. Here we're talking about exterior acoustics. And, I should state before I get going, I've always covered either the country or several countries for the jobs I've held. There have not been a ton of exterior acoustic people. There's some out there. There's people who deal with it. But it's my understanding that to become, I guess, what you would call an acoustician, you basically are an engineer. There's really no undergrad acoustical degrees. Maybe there is now, but 20 years ago when I was first getting into this, there really wasn't. And people just kind of got into this. Then they got an acoustic MBA. And most of that was aimed at interiors. So you're doing theaters, or we'll take Vegas, for example. All the people I knew in Las Vegas did, inside of casinos, theaters, convention halls. Maybe if you were rich, you had a theater in your own home, bowling alleys. These were the things they were focused on. It was very hard to find someone doing acoustics for exterior. Now I go to Vegas and I know of at least 6 companies doing exterior acoustics. So definitely with the population growth, this has become a thing. Where there's a problem is the test requirements. They're still based off of interior acoustics. And again, I'll show you that as we get going, so you have a better understanding of kind of where the whole industry's at right now. So again, basic outdoor fence type stuff. and you're all familiar with this, so I won't go into too much detail. Now, there's different types that have been used for exterior acoustics over the years, and it really depends on the area that you're in. Again, I've covered such large areas. In the Southwest, concrete block has been the big one, and they base a lot of things off mass. I get up in the Northwest, a lot of it's wood. Minnesota, even their sound walls up in Minneapolis for the highways are made out of wood. And of course, there's positive and negatives to all of these. You can get an acoustic rating, but as wood bows, you can start to get gaps. And then, sometimes fire ratings are an issue, but that's a whole nother thing for exterior. So different products have different positives and negatives. Wood, for example, as you can see in these pictures here, it's less expensive. It looks great. I love the look of wood, but as you can see, the gaps are on here. And in a lot of places, and a basic overall rule when I talk to acoustical consultants is, if there's any areas you can see through, it is not considered a sound wall. So when we're talking about outdoor acoustics and sound walls, if you can see through that, it would not be considered a sound wall, according to kind of just like a rule of thumb. Then there's vinyl, which we also manufacture, but I do not recommend vinyl as an acoustic sound wall, or it can be used depending on what you're trying to do. But it's low maintenance. Everyone's familiar with it. The problem you run into with vinyl is once you start getting into height, which is very important to acoustics, and getting up over 8 feet tall, there's not a lot of manufacturers that make vinyl over 8 feet tall. Now, there are some that make very expensive specifically for acoustic sound walls on highways or things like that. But you're getting into products that now have additional materials added in and things, and those costs could be double or even triple what we're talking about today, double the cost of block almost. They're good for what they do, but they do become expensive when they start making vinyl into tall acoustic sound walls. And then we have wood plastic composites. So you're all familiar with composites. And one thing I should mention is the product we're going to talk about today, people think is a composite, and it is not a composite. It is 100% polyethylene. So I'll talk about that a little bit later. But it does look very similar, one of the styles, to the composites that you're probably pretty familiar with seeing. Now, the issue with composites, again, is there are air gaps typically. Now, maybe they'll make changes to fix that, but currently there's not a whole lot of composites that are considered sound walls. And then, of course, concrete. Now, concrete is great for acoustics. It's used all over, especially if you're near train tracks, and there are definite applications for concrete. But again, there's positives and negatives. Graffiti removal would be a negative to the concrete. I'm sure you all see that everywhere where it's spray painted. However, concrete bases its sound reduction off of mass, where we do not. Ours is based off an air gap, which I'll explain. So the cost of installation, but again, if you're going to need a really high sound rating to reduce sound, maybe you're next to train tracks or right off of a highway, you may need to use concrete or even block in some cases. And here's block. Everyone's familiar with that. The only negative I can say with block is that the price really changes around the country. In the Southwest, it's very inexpensive. When you get up to the Northeast, it's very expensive from what I see. So depending on where the job is going to be, that's something you have to factor in. So if you've done a job in Phoenix and then you're going to do a job in Chicago, say, it's two totally different things in terms of price. So just keep that in mind if you decide to go that route. And then polyethylene, what we do. So we make stone and we make wood. And again, the pictures show shorter walls because that's how we started out when we made this presentation. Typically, when we're stacking these panels up, now we can go up to 18 feet high. The stone is the one everyone goes for. It's probably 95% when it comes to high sound walls. So, and the reason, if anyone's ever interested in considering this product, is when the wood is stacked up, it looks a little bit wonky because of that mid rail that's in there. You don't see wood stacked up that high really. Up to 8 feet high, wood looks good, but stone is what everyone goes for on the taller walls. Polyethylene is basically the easiest way to think about it is the gray garbage cans that you roll out to the street that seem almost indestructible. That's exactly what this is. There's LDPE, which is a low density polyethylene. That's what we make. And then there's HDPE, which is the super glue bottles where it's hard to squeeze. They're kind of rigid. So there's two different types. It doesn't really affect the product and its performance much. It's just one's flexible, one is not. We decided to go with flexible due to rocks hitting it and things of that nature. Now, one thing about polyethylene, and especially our product, is this is not a retaining wall. I get a lot of requests about this. People think it can also be used as that. It cannot hold a lot of weight on top outside of stacking panels, which it is intended for with the type of beams that are used. So if you had a project and you wanted it to hold weight, do not use it for that application. You can mount it on top of retaining walls, but do not put anything on top of the product itself. Oh, one second. My screen's kind of blocked here. Sorry. Oh. So what is polyethylene? As we talked about a little bit here, extremely durable. It does not fade almost at all. I cannot say it doesn't fade at all, but it's about half of one Hunter unit over the lifetime. A Hunter unit, if you don't know, is how they measure fade, basically. We've had polyethylene installed in Las Vegas for 10 years in our darkest colors, and we've replaced panels, and you cannot tell which panel's been replaced. So polyethylene is great, especially in southwestern or southeastern states where it gets real hot, because then it just won't fade there. Additionally, vinyl will soften and sag, if you were thinking of that product, around 120 degrees, whereas polyethylene has to get up to about 160 degrees before it starts to sag. We say 140, but that's just to be safe. It's really more around 160. Weather resistant, as we said, the heat doesn't really affect it, doesn't fade. Water doesn't affect it. There's no wood as there would be in a composite. Bugs do not get into it. They don't like it just because it's 100% plastic. And one thing I should mention that I don't think is in this presentation is polyethylene is not made using petroleum. It's made using natural gas. And then also we had the colorant in. So that is it. There is no petroleum. If anyone's concerned with that, I know a lot of government jobs. That's something that does come up, but there's zero petroleum used in polyethylene. And again, low maintenance. Because it's the same material that they ship super glue in, nothing sticks to it. And just real quick, that's because the molecules are too tightly bonded in there. So I won't get into all of the technical stuff about the chemistry on it, but that is the reason nothing sticks to it. So spray paint, graffiti, I'll talk about in a second, can easily be removed using a power washer. So this is the picture that I like to show. So this stands for Salt Lake, Utah rules. Again, we make it near Salt Lake. You can see here, this is actually a sound wall that was put next to an apartment complex in a road. It was spray painted. And I think about 2 days after it was spray painted, they used a power washer, no solvent, nothing else was used, and just hosed this down. And you can see at the bottom where all the graffiti came off. This is becoming a big issue, especially on sound walls in California. So if anyone's on the call from California, I believe it's called Tile 24, where you have to have some kind of anti-graffiti layer on the wall. I know people are spray painting like a clear coat, and then they peel it off after it gets tagged. I don't have any pictures, but we did a car dealership in Los Angeles that was getting tagged all the time, and he put one of these fences up. And every day he would get up in the morning before work and hose it down. And after 6 days, they quit tagging it just because every day he would just take it off with no problem. So we can't say it's 100% anti-graffiti. And the reason for that is if this product is left in the sun with the graffiti on it for a month, say in Phoenix, and it kind of bakes on there, you can still get it off. But at that point, depending on how hot it's been, how much time in the sun, you may need to use a solvent. You may need to use some kind of like copper bristle brush or something to kind of scrub it off. It will still come off because we just did one in Orem, Utah. The city built a new road where they had our sound wall up. They removed it and gave the wall to some people in the neighborhood, but they had to clean off the graffiti that was on there and had been on there for about a year. So that was kind of a tough one to clean off, but we were able to do it. So the graffiti will come off, but the sooner you get it off, the better. So polyethylene, all polyethylene is made in a rotational molding process. So I like to bring this up because people think plastic is plastic. When you make vinyl, people can kind of envision it coming out in slats on a conveyor belt. That is not how polyethylene is made. So if you think about things that are made from polyethylene, think of canoes or kayaks. The garbage cans I mentioned, there's usually one hole within there. We also have a little hole on the side of our panels, and that's for the off-gassing. But polyethylene of all kinds are made in a rotational molder. And the best way to think about that is as if it's a big waffle iron. So those three arms sticking out would be the size of a panel, the big squares. That's a panel in there. And that rotates and spins and goes through a furnace and heats. And the polyethylene powder sticks to the outside. So just like kind of like a waffle iron is done. And then the interior of those panels, we have a patented system to keep the sides together. It doesn't involve any extra material. It's just the way the molds are made. And and then we have the air gap in there. So this is what a final panel would look like. It slides into an H groove. And as I mentioned, we can't have any air gaps. They're solid. We do not sell polyethylene in slats. It's all solid privacy panels, and they slide into these H grooves, so there's no air gaps, so sound can't travel through there. Polyethylene, our test that we've done in Utah, we've tested it down to -40 up to 140, all different kinds of chemicals. This product itself has been around since 2004, and over time it's changed, and there's been new testing and kind of stuff. The last owner of this product was a company called Saint-Gobain, who I worked for. You may know the name Certainteed. Some people know that name better. But Saint-Gobain was the parent company. They are based out of France. They own one of the largest adhesive divisions in the world. So that's all they make. A few years ago during COVID, when we were all locked inside, we sent them samples of polyethylene and asked them to find an adhesive that would stick to it. They could not find anything. They thought for sure they would find something because that's what they do out there. And they're known for glass and adhesives in Europe, glass mostly in the US, but they could not find anything that would stick to the polyethylene. So bugs, we say salt spray if you're near the ocean, salt off the roads for cars is a big deal. I've recently been finding out that's been a big question I've been getting. So things of that nature, nothing will stick to it. So if you're worried about cleaning it or dirt, which I went to a DOT convention called NoiseCon, and I was very surprised how much of a concern that was to all the engineers who work for the states and do a lot of the highway work. But nothing will stick. It's very easily to clean off. Recycled content, this kind of varies. It depends if you have a closed loop plant. For those of you who don't know what that is, a closed loop plant basically means there's almost no waste. Say you grind off some of the polyethylene when you're manufacturing the product, that grind off is going to be reused, melted down, turned back into powder, used again on another panel. But then there's also people who are concerned with what we bring in, raw material that is recycled. What we say is about 20% of the new material is polyethylene. But then we also have a closed loop factory where we don't waste almost anything. So when you factor that in, it can vary. It gets a little complicated. And I always recommend everyone, when you hear these recycled content numbers, there's really a lot you can dig into. We have more recycled content in our posts than we do in our panels. I don't know the reasons for that. So the post might be 50%, the panels might be 20%. 20% is a rule of thumb on new recycled material, whereas in the factory, the amount that we recycle and reuse is a higher percentage. So it gets a little more complicated than just saying we have 50% recycled. And I always recommend to people to look into that. Part of the reason is, there's been people who've made videos where they've put, iPod trackers into recycled plastic bags that are supposed to be going to a place to be recycled, and they end up in, some dumpster somewhere. They never actually make it there. But people are saying they're recycling this stuff. You don't know for certain. I've heard that in reality, 5% of all plastic that is intended to be recycled actually gets recycled. Um, so the good thing here, though, is we're using natural gas. We're not using petroleum. So from the beginning, we're doing all we can in terms of plastics to be environmentally friendly. So now we'll talk a little bit more about acoustics of polyethylene. And again, some of you may be very familiar with this. This is a very basic overview of acoustics and the definitions of sound and kind of what to look for and think of. Part of the reason for this is when we talk to people, including architects who are not that involved in sound, but maybe they have a sound project coming up. A lot of times it's general contractors who don't understand acoustics. We have to go in and kind of just talk to them a little bit, give them the basics. So I apologize if there's people on this call that are heavily into acoustics, but for those of you who are not, this should be pretty easy to understand. So weight is one of the big factors when it comes to acoustics. We talked about block with mass. There are certain parts of the US and Canada, and really big in Eastern Canada, where if you were going to put a sound wall up, nothing matters if your product doesn't weigh so many pounds, I guess in US terms, per square foot. We've made products that are heavier. They don't work as well in terms of failure rates. They're too heavy. And part of our whole thing is a lightweight sound wall. But in Eastern Canada, somebody went up there, probably a manufacturer's rep, talked to somebody who wasn't that familiar with acoustics, and everything has to weigh, I forgot, I think it's like 16 pounds per square foot minimum, which if you're considered a lightweight sound wall, you're between 4 and 5 pounds, I think it is, per square foot. So in Canada, Eastern Canada, we don't sell almost anything up there. And that is because there is a perception you have to have density. Now, that being said, two things to know about density. One, sound travels through dense material better if you physically touch it, which will not necessarily be the case for the applications here. If it was an interior product, it might apply more. The other thing is, when you come to density, it will block more sound depending on how dense the product is. So we will block what's called 26 STC, which I'll get into, whereas block, I don't know, it might be up to 55 or even higher. So you're going to pay more, the installation's more, but if that's an application you need, well, then that just may be the way it is. You may have to find a dense product. Then height. I called in a big time acoustic engineer for one of the biggest firms in the country just this week. And I'll be meeting with him to go over a new product we make here in about a month or so. And it's a 10,000 person civil engineering firm, but he's the head of their acoustics division. And the very first thing he said to me when I called him was, well, height is what we really care about. So that was, forget everything else. If the product is not tall enough, if it can't be stacked high enough, if it cannot be mounted on top of other things because it's too heavy, whatever the reason is, then it's not good for a sound wall. It may be used for a commercial application, really. You may be able to use it in someone's backyard. You may be able to use it for minor applications, but if you're doing, around a factory, off of a road, big applications, height is probably the number one consideration, as well as air gaps. Those two things are probably the two most important, regardless of the material, regardless of the density, all of that. Height is probably the number one thing, that and the air gaps. And then the structure, as I just mentioned, the air gaps and things like that. Like I said, when I'm in Minnesota or when I go around countries, and this is just reflective of, I guess, people not fully understanding acoustics and how sound travels. When I go to Minnesota, and Minneapolis and St. Paul, all of the sound walls are wood. And there's all kinds of holes where the knots have fallen out, where the wood has deformed. They look nice, except for where they're spray painted because they can't get that off. But originally, I'm sure they looked great. But then I go to Atlanta and there's sound walls all over the highways that are made out of metal. So it's the complete opposite. And then I go to Arkansas and they're vinyl with a whole bunch of other stuff added in. So the sound wall market in terms of highways, which is really the big one, it just varies nationwide, and there's not really a uniform kind of consensus on what works, what doesn't work, what they should do. Some people want something that looks good, maybe that's their top priority. Other people want, maybe something that doesn't reflect noise or maybe has a different sound rating because maybe they're more familiar with interior and they're focused on, whatever's required for an interior application and they're using that exteriorly. So there's a lot of confusion within this market, but I do see it definitely growing. There's a lot more interest. I probably say 90% of the calls that I get relate to acoustics. Even though we make fence for all applications, we make aluminum, we make vinyl for whatever you need. 90% of the calls I get from professionals are going to relate to acoustics in some way. So then we'll get into frequency and decibel a little bit. So frequency will be the speed of the sound wave. So to make it easy, is it a shrieking sound or is it a low, deep sound? So the shrieking sound, real squeaking, that's going to be fast, and the deep sound will be slow frequency. And then the decibels easily is just by how loud it is. Oh, 1 second. My screen is blocked here. So this little picture over here is just showing to give you a better understanding of how sound travels. We talked about the density. If you put your ear to the ground, this is supposed to be the buffalo coming. He can hear them, but the person standing up cannot hear it through the air. So when I talk about density, that's kind of a good way to think about it. That sound will travel through dense products when you touch them. So now we'll get into STC and some of the other sound ratings. STC is the main one. It's the sound transmission class. And from my experience, I see STC ratings, for people who are maybe not that familiar with acoustics, but they're being told, hey, you need a certain STC ratings. This is what they know. They know I need a certain number as an STC without really understanding why. I say this, we have a good STC rating and we're being used everywhere. We don't have any issues. But when I speak with people, there's a lot of confusion on this, and the test methods are confusing also. So I highly recommend, if you are specifying any type of sound product, that you get a full understanding of the STC ratings, because that's the number one method that people use to judge a product to block sound. But it is definitely not the best method, at least for exterior products. But I just had an architect call me from New York. We're doing some Starbucks drive-throughs. He had a different application and he said, hey, I need a 30 STC. Now we're a 26 STC. So to give you an example, he needed a 30 STC and a sound wall that could go up to 16 feet high, I think it was. In Colorado, they require 20 feet high and at least blocking 8 decibels for a sound wall. You can block 8 decibels depending on several factors. How loud the original sound source is, how far away the sound is coming from. There's a few things you have to add in there. But to block 8 decibels of sound doesn't mean you have to have a 20-foot high wall. You could have a 12-foot and 8-foot, it just depends, and save a lot of money. But someone who wrote the code in Colorado somehow thinks you have to have a 20-foot high wall in order to do that, which is a very expensive sound wall. So this architect I talked to in New York was in the same type of boat. They needed a 30 STC, but the amount of decibels that they were trying to block, which is the real factor, the thing you want to think about, did not require a 20-foot high wall. It could have been done with a 12-foot high wall probably. So you could have probably cut your cost in half on that wall. This architect was stuck though, because he didn't want to go back and get everything changed, didn't have enough time. So he had to find a product that was 20 feet high and had a 30 STC. You could have a 20 STC and block 8 decibels depending on, again, where the sound's coming from and all that kind of stuff. And this is where it gets a little complicated, and why saying I just need a certain STC number is not always the best way to go. Now, there's other type of test classes in here that I have listed. I won't go into all of these, but there are definitely better test methods. The STC rating is not a test, and I'm going to try to get to it real quick here. this is how it's tested. This is our product being tested for an STC rating by ASTM. So you probably notice here, they'll shoot the sound directly at this panel. This panel is sealed in inside of a room with a roof. So basically I have written over here, it's tested in a vacuum. This is not realistic to real world applications outside. So as I mentioned in the beginning, the test methods are still catching up, I guess. Now, there are field STC ratings. So there is an exterior test. I have never seen anyone with that listed on anything. I'm sure it's out there somewhere. I've never seen a company promote that. And the reason is, since everyone is using this method, which will give you a higher STC number, if we took our panel and then tested it outside, our STC rating, I don't know what it would drop down to because we've never done it, but it would be much lower than a 26. So at that point, we're now missing out on jobs where someone says, hey, I need a 25 STC, and that's all they know. So to this day, the STC rating is intended for interior products, but it is basically the standard for exterior sound ratings. So if anyone ever has questions on that, call me, because I try to be involved in these test methods, because a lot of them are intended for interior products and they're way behind on catching up for exterior. But hopefully that was clear. And as you go forward, if you're going to specify something as an exterior application, I don't know if you work with developers who do perimeter walls or anything, this is something that needs to be factored in. And again, this doesn't take into account the height. There's a lot of things that go into it. So right here, you'll see the STC ratings of different types of products. So wood is going to be a 16. Now, this may not be accurate, but this is what I've been told from acoustical engineers, some big firms. If it's a 17 or lower, it really doesn't count as a sound wall. I don't know if that's true technically. That's just kind of what I'm told is the rule of thumb within the industry. So you can see composite fences, and I've known some composite companies that promoted 17 and then took it off their website because they realized it really didn't block any sound. So that may be accurate. Vinyl fence is about as low as you would go. Then, of course, concrete, and then there's us. We say 23 to 26 because the wood is a 23. The stone is a 26. And the reason for that is the stone has pointy edges and it breaks up the sound as it travels at the sound wall. So, but there's the differences. You can get an idea. And again, concrete block and masonry, of course, that's a great one, but it does bring additional costs with installation due to the weight. So regardless of the STC rating, another thing that you have to think about is the type of material. So as I have listed here, gypsum as a 29 STC used in your house. 26 would be just a thin steel sheet. However, the frequencies that are coming at those products greatly affect how much noise is blocked. So gypsum will block people talking, say, mid to low range tones, whereas a steel sheet will not block that very well. But if you had a high shrieking sound, something on a pan in the kitchen or your fire alarm squeaking in your house, the steel sheet blocks that better. So not to get confusing or too far into this, the actual type of material will also affect what type of sound is being blocked. So we want to focus as an exterior sound wall company on mid to low frequencies. We didn't know this when we started it, but we went and had the product tested and we got lucky. That's what we block. If it would have blocked better with high frequencies, we really wouldn't have had an application for it being used outside. Of course, you're going to get some high frequencies, but the majority of the sound you get outside with cars going by, dump trucks, people talking, that's going to be mid to low. And that's where we perform well. So again, I'll skip over some of these, not to get too technical. As I mentioned, these are the type of noise that we block here. Airborne sound. A big concern that I've been seeing with these sound walls is tire and wheel noise. So when I say wheel, trains. We will be installing these panels up in Seattle, it looks like, on the expansion for their train. They're worried about sound coming off of there. When I was at the NoiseCon convention, the engineers were very concerned with tire noise coming off of the roads. So that surprised me that that was a big concern there. So we reduce sound using air gap. This is becoming more and more of the way people want to do it or companies want to do it. And part of the reason is it's less material. So there's less cost involved with it. And then installation wise, there's less cost involved with it. So an example of that is the state of Ohio, unknown to us about 3 years ago. We had no idea this was taking place. Hired a third party firm to test our panels, which are done with air gap, versus concrete panels, which are solid, off of roadways. They went around the country and would test us where we were already installed. They even installed some of our own panels next to existing concrete panels. And what they found was at 8 feet high, we blocked the same amount of sound as a concrete panel, but we were half of the cost with installation. And then when you went up to 12 feet high, those were the two heights they were testing. We blocked the same amount of sound, but we were about 25% less. And that's because now you need some equipment to install them when they get that high. So the air gap will block the sound as good as some uh, dense products. Again, though, if you have really thick, heavy block, you're going to probably block more sound. But it depends how much you need to block. Do you always need to block? Do you need a 55 STC? You may not even need that. So in homes, you have the air gap between walls. And this is just an example here. That's not just for insulation purposes. It's also to reduce sound. And I found out, which I had no idea, that India has a car industry. I didn't know this. And I guess they've been doing a lot of testing, or they did a few years ago, on mass versus air gaps in the floors to reduce sound off of the road from the tires inside the cars. And they were going in the direction of an air gap, of lightening the floors and having some kind of gap in there that would absorb that sound, rather than making the car heavier with mass, which would of course increase cost, and I guess gas to drive it around would be more, things like that. One thing to note when it comes to sound is that sound likes to travel diagonally upwards. So at the beginning, I had mentioned height was a very big factor. This is the reason. Height will travel upwards. Now, without getting too complicated, of course, as you go back further, the sound source further from the wall, the sound will reduce some as it reaches the wall, but it will also go higher because you have a further distance to travel up. So the best way I use to think about this is if you were on one side of a wall and you were spraying a hose over the other side, that water coming out is the sound. And as it goes over the wall, it kind of drizzles down on the other side. So if you picture it that way, moving back and forth towards the wall, that's kind of how sound travels. So again, when you're designing a sound wall, you don't always have to have a really tall one. When we're doing the trains, 4 feet high, because the wall will be closer to the wheels of a train than, say, a sound wall, typically 16 feet high off of a highway. Those walls are going to be further away. The closer you get, typically the shorter the wall can be. Here's an example of just different heights we do. That's a 12-foot wall around a parking lot at a Kroger's, just to give you kind of a visualization of what one of them would look like. Installation, again, when you talk about density, it's far more expensive. This is one of our panels being installed. You can see it just takes 2 people up to 8 feet, and that's because the panels weigh about 4.5 pounds per square foot. So it's not that hard to install. Where that comes in handy is if you ever have an application where you need a lightweight sound wall. Lightweight sound walls are typically going to be between 4 and 5 pounds per square foot. Not every application needs those. A lot of times for bridges, you would need a lightweight sound wall. There's other applications. So that's the opposite of density. You're going to want a lighter product, and that's where we fit in well with our product here. Being that it's a lightweight product, you can mount this with concrete footers. Just a picture right there of how that's mounted. You can see this. I won't go through all the details on these. And then I'll summarize here before I talk a little bit more details, just a couple slides about our product. So again, it's lightweight, anti-graffiti, insects, not corrosive, maintenance-free, We used to say completely rocks won't fly up from a lawnmower and break it. Again, it has a little flex to it. Doesn't warp or fade. Paint won't stick to it. We do meet Miami-Dade wind code with this right now, not necessarily on the footers. The way they test that is when the beams are into the ground and they're testing to see where that beam breaks. Basically, it's always going to be right at the ground level. UV and 12 inhibitors are one of the few, that and colorant are the only things added into the mix of the polyethylene. And then I'll show you the wood and stone patterns that we have with the different colors. So we are now called Catalyst, our product. And I think I have about 3 slides to go over here. It gets a little confusing because people out there who may be familiar with this product know us as Simtech, we were Saint-Gobain, and then Certainteed. Now we are owned by Oldcastle. Oldcastle has rebranded. There are a bunch of divisions. I'm being told the name Oldcastle may actually be rebranded. That may go away, but I haven't heard 100% yet. But we are now called Catalyst. They still say Fence Solutions, but we are also doing the sound walls. This is what we call Boulder, so the names of the products have also changed. This used to be EcoStone, so now it's Boulder. If anyone has questions, if you have a project where you need to use this, feel free to reach out to me. We have a million specs out there under 5 different names. But now everything will be Catalyst going forward, and hopefully this is it for a long time. Boulder is the new stone product. This one is a picture where did a parking lot around a McDonald's. We also have the wood, which is called Breckenridge. These names work out great for me because I live in Colorado, and those are 2 towns in Colorado, so I can remember them pretty easily. This is basics we've already talked about. I am basically the acoustic kind of point man for everything that we do. If you have questions, as I stated at the beginning, I can at least speak the language and understand what's going on in the acoustic environment. I am not an acoustician. However, I do have a simulation that we use, and it's been used probably 4 to 5 times, and we've won every single one of these where, I'll give you an example. Starbucks in Queens, New York, we had a lot of uproar from the community because they thought it would be very loud. It was an old burned down Burger King for one of these. It had grown over with trees. It was kind of just like a forest, and the people liked it. Well, now Starbucks bought it, and they're putting a drive-through in. Of course, the neighbors and all the people around wanted a gold wall, palm trees, 20 feet high. They didn't care what it cost. Starbucks came to us, the architect came to us. We take a little bit of information, as I mentioned earlier, and we can get it pretty close, usually within 5 decibels of how much noise will reach the homes, the office, whatever it is. We do a lot of doggy daycares where this is involved. And then we can tell them, look, yeah, we meet all the codes, city code, federal code, whatever it is. If you go this height for this type of sound wall, it will block this many decibels, and this is how much sound will reach the people that are complaining. To this point, once we've done that, we've won every single job and been used on those, and the cost compared to what the community wants put in, maybe 10% of what they wanted. I'd say for sure it's at least 50% in all applications, but there's a lot of times it's far less than what everyone's asking to be installed. So if anyone has a situation like that, feel free to call me. These are the colors we make the product in. They're all going to be earth tones. These are the colors for the wood, and it does look like real wood. You can tell by this picture here. We even had a person call us recently that thought they were going to get splinters from it, but it's just plastic. We do make gates also. Gates can be fabricated. Of course, the gates will not have acoustic rating due to these gaps. I mean, the panels have the same rating. So technically that STC I told you about is the same on the gates. But as you can see, there's a lot of air gaps in there. So those would be more for residential. The panels slide easily to these H grooves. It's not complicated at all to install this product. Now, what we're doing now, most recently, is I don't even have a picture yet of the final product. We are making a more industrial and commercial type of sound wall because we're seeing a lot of these projects come through. The black is powder coated aluminum, and the panels sit in H grooves on the inside. And what this does is it prevents any possibility of bad spacing of the posts on installation because plastic likes to expand and contract a lot and can cause the panels to bow. Also, the weight of panels up on the top, the higher panels, may over time start to weigh down. If you get to a 16 or 18 foot, could start to weigh down on that bottom one if it's not installed correctly. If it's installed correctly, you're fine. But a lot of times guys don't, they cut corners. Well, this prevents that also. So we're going to start going up to 18 feet and 16 feet with this system here. We installed the first one this month. I was told they're tweaking a few things on it. So within the next month, it should be available to go. And the cost is about 4% more than our old system. What's also nice about this is you no longer need the large H-beams, which were very expensive. This is done using, because we make AlumiGuard aluminum fence, and that's about a $500 million market for us in our sales. These are, I believe they're 18-inch long sections of aluminum. I could be wrong on that. It might be 24, that are bolted together. We've done all the testing, the wind code testing, all that kind of stuff. They bolt these together, which means now we can ship those very easily without having to ship full length H-beams. And that's pretty much the end of the presentation there. So if anyone has any questions, I'm happy to answer them now, or if you want to write them in later. But that's all I have. So thank you everyone for attending. Hopefully that was informative.
Thank you so much, Spencer. We do have a few questions here.
Okay.
The first question is, how resistant are your sound walls to wind load?
Well, we're Miami-Dade wind rated. So I mean, I guess that's the best way to put it, because that's basically the cream of the crop for testing. Now, what I will say is Miami-Dade is changing their codes, I think, in 2 years. So we'll have to get retested. But at this point right now, we are rated for Miami-Dade.
Awesome. Next question is, given that sound can move around corners, can you address how you can determine the height of an acoustic wall based on the sound source location?
Well, I know it can snake around, and that's something we've been looking at. But again, when we see these projects come up, and we're not an acoustic company, so we're not out here, we're not the acoustical consultant. We get specified by a lot of them, and I know a lot of them, but we make a product right now that is aimed at meeting the codes. So again, you need a certain STC code. Okay, we've done the testing, that's what we have. But we haven't gone out and tested what goes around it or different ways sound can get around. What we've done is go out and say, these are the tests that are required by either DOTs, by, private companies, what they're trying to do, and we've met those requirements. If it was very important that you had to know, okay, how much sound will kind of snake around the sides of it and that, then you'd have to bring in an acoustical engineer and we'd have to work with them and figure that out. But to tell you the truth, I couldn't even tell you without curving the ends of those walls. And we haven't had a project come up where that was needed yet.
Thank you. Next question is, I understand the need for solid walls for sound, but how does a solid panel handle from a structural standpoint in wind loads?
You said wind loads, is that what you said?
Wind loads, yes.
So yeah, so the same thing, we're Miami-Dade rated. Now, when I say Miami-Dade wind rated, the test that Miami-Dade does is 8 feet tall. They don't have a test above 8 feet tall. So if you were going to go 12 feet or above, which we do, we have multiple 16-foot high walls out there right now. A lot of them seem to be in New Jersey for some reason, but you definitely, that would be an in-ground, not a concrete mount application. You would put the beam in the ground. Our panels can come out at super high wind loads. So say you had a 130-mile-an-hour wind load, which is above Miami-Dade. There is a chance that a panel could come out, or even if a car bumped into it. Now, there's positive and negative to that. Number one, that panel can just be put right back in. It doesn't ruin the fence, so you won't have any cost there. Because we have a guy in Miami who, before hurricanes come through, he takes all the panels out. This is how easy they are to take in and out. He goes to all of his visible jobs, takes all the panels out, puts them in a warehouse. Then he puts them back in right after the hurricane passes, and he gets all kinds of business because, people think, oh, they get damaged at all from the hurricane. That being said, we have walls up near Fort Myers where the most recent hurricane hit, or maybe it was two hurricanes ago, and our wall withstood that. We had no problems. So we've used those in like case studies, or they're creating them right now. But I cannot say above 8 feet exactly what the wind load would be because Miami-Dade doesn't test for that.
Thank you. Jack asks, "What is the fire? What is the fire spread? Should there be a wildfire or traffic accident starting a local fire? Also, what is the hail rating?"
So the hail rating, I don't know because we're about to test that. That's something we're coming up, the impact rating on that. I have no concern at all that we're going to do fantastic on that test because we have actually paid professional baseball pitchers that pitched in the World Series and golfers to come and hit balls. We have a video on this, if I could find it. If you'll write in, I'll send you a copy of it. But we have a video where we had them do this, and there's no damage. The balls just pop right off. So we're not worried at all about hail, but we are going to get that impact test done. We don't have it yet. So that should not be of any concern. Now, the fire rating, I have pictures of the product during the Paradise fires in California, Northern California, like 8 years ago, whenever it was. And we don't have an official fire rating, and there's a reason for it. So if you go online and you look up polyethylene, you'll see it's Class B fire rated. And we don't actually say that. And the Paradise fires, we have pictures of where the panels melted. So they will melt for sure. Um, I haven't seen any go up in flames. The problem we're having is we sent panels off to be tested for a fire rating about 3 months ago, up to a firm in Chicago. As I mentioned throughout this presentation, all of the fire rating tests are either for floor or ceiling assemblies. We have not found anyone who does an exterior fire rating test that takes into account wind flow and things of that nature outside. So as I said, also, you have Minnesota, they have wood, which is definitely not a Class A or Class B fire rated product. So it's kind of weird around the country, what people are concerned about. We want to get this tested. In order to get polyethylene to a Class A fire rating, you add chlorine to it. That's all that's required. So I don't know how much chlorine you have to add in. I don't know if it will affect, the makeup of the product. We have to change a lot of things, but that is why vinyl is Class A fire rated. It naturally has chlorine chemical in it or molecules in it. That gives it the Class A fire rating. Polyethylene does not have that, so we would have to add that in. However, we're trying to find a way to get a test done. The reason they couldn't do it in Chicago is the plastic melts and it was clogging up their equipment. So they had to cancel the test. So that's kind of where we're at with that right now. The thing that we have as a positive is we're not using this interior. It is an exterior product. In most cases, it doesn't touch a building. So we haven't had a lot of issues with it. But as government jobs become more and more, some states do want that Class A fire rating. So we're trying to figure this all out right now.
Excellent. Thank you. David asks, "Are there limitations to the gap size at the bottom of the wall?"
Well, typically sound's going to travel up. So that is your least area of concern with the sound, unless you have, the sound source right next to the wall at the bottom. So I would say if you're worried about sound traveling through, that's the last thing you're worried about, unless it's a huge gap. If you got a little inch there or something. Most people, when they're concerned with that, they try to get it directly on the ground. This product can be buried. You can pull it up in 100 years. It won't affect it. As I said, bugs, chemicals do not get into it. We can regrind it and reuse it in 100 years. In Baton Rouge, Louisiana, they've actually buried it completely. You can't see it in front of dugouts of baseball dugouts because the fields keep flooding and water keeps getting into the dugouts. So they put it in front of there to block the water so it goes around the dugouts. But it won't harm anything. It's environmentally friendly. Nothing leaches out of it. Again, it's made from natural gas. So I would say if you're concerned, if you can bury it, that's the best way to do it. But if you have to mount it with concrete footers, just don't have a huge gap and it should be a huge concern.
Excellent. Uh, Carter asks, "How old is the oldest installation of this fence material?"
I think 2004. We got a whole bunch from 2004. That's when the company was founded. That's when it started.
Excellent. Ted asks, is installation sill sealer required at base?
You don't need anything for the installation of this. Just the fence and the post. There's no sealers or anything. If you're concerned with like possibly two panels butting up and maybe having a gap, if that's what you're referring to, this product, and I'm not talking about the new system with the aluminum, but the system where maybe you have two panels butting against each other, it takes about a month, depending on how hot it is. And those panels mold together and basically seal off any gaps or any open areas that would have been on the top or the bottom there.
Bruno asks, are samples available?
Oh, sure. Yeah, if you'll just write me and give me the address and everything, I can get samples sent out to you.
And also, everyone, when we review the session code process, there is an option for you to request samples when you're submitting session code. So we're going to go over that shortly as well. Carter asks, what is the warranty?
It's a lifetime warranty on the product. Now, that's for commercial. I don't deal with residential. I'm not 100% certain on the residential warranty if you get involved in that. But it's a lifetime warranty for commercial.
Awesome. And Joseph asks, what is the weight per square foot of the polyethylene wall?
It is somewhere, depending on the one you use, between I'd say 4.2 and 5.2 pounds. It just depends if you're using the wood or the stone. But it falls in that range, which again worked out good for us because I work with some large acoustic firms that want panels that have some mass, but they don't want them to be over a certain weight. Because I think if it gets over, I could be a little bit off here, 5.5 pounds, it's somewhere in that area, then it's no longer considered a lightweight sound wall. So we're under that, and I think we're just over 4 pounds.
Awesome. Vladimir, yes, you are. That is coming up at 12:05. Brian asks, how well does the product perform with sounds generated by pickleball?
Oh, we're actually used on some pickleball courts. I'm not saying we're the absolute best to be used on them, but we are. Some sound will reflect a little bit into the court. That's my only concern, but no, they have us on pickleball courts up in Washington State that I know of.
Awesome. Jack asks, not only fire spread, but toxicity of smoke. What is it?
So I can't give you any technical info on that, but I can tell you this. With the Paradise fires, when that all happened, the fire department came to us and there was not to talk bad about competitors, but there was a composite named Trex, you may know them, that was used extensively in that area. The fire department reached out to me because the smoke coming off of the composite was making the firemen sick as they fought the fire. But the smoke coming off from our fence where it was used was not making them sick. So they wanted to learn more about what we had and what the product was. So I can't tell you because I don't know if we've ever really tested it. But I do know that, well, that's basically the information I have on that. That's not a question that's come up too much. But again, polyethylene itself, we have done an HPD, a health product declaration. So that is available. If anybody wants to see that, I can get that to you. And we're about to do an EPD, an environmental product declaration. Of course, that takes a lot longer. It's about a 6-month process, but we are going to have that done. So, but I can give you the HPD, and that should have a lot more of that technical type of information that maybe will help you out if you want it.
Awesome. We do have a few minutes for a few more questions, but some of you are posting your questions in the general chat. Please do not use the general chat. Please repost your questions in the Q&A so they could be included in the Q&A report. Thank you. Haiti asks, what is the required foundation for the 18 feet high wall?
So the 18-foot high wall is the new system. That's the only one that can go 18 feet high with the aluminum framing around there. And that's a hard one to state, and I've been dealing with this for years. It's because of the soil types and the wind loads of where you're going to be. So we work with a lot of large civil engineers, one being a company called Stantec. Their roadway division is in, or at least one of the roadway divisions is down in Charleston, South Carolina. And I think it was 2 years ago, the state first approved sound walls because the population's growing so much and it's getting loud off the roads. Homes are moving closer to the roads. And when we went down there to talk to them about this, that was the first company that ever asked me to have drawings specifically for their soil type. It's sandy. It's not real hard like maybe you'd find in Arizona, and it's very windy on top of that. So all of the companies that we know of, and even ourselves, we have recommended, depth installations and the type of post you should use, but that's all based off basically Midwestern type of soil, moderate wind loads. And I do get a lot of calls from engineers asking us, to test the soil, which we don't have someone who flies around and just goes and tests soil. That's their responsibility to do that. So it's hard to definitely answer that. You would have to know where this is going to go up, how firm that soil is, what the wind is. There's a government site that gives you basics on all of that kind of information. And I'm trying to have different drawings that specifiers can just put into their designs for the different types of wind loads and soil types around the country. But even that would be an estimate. So it's really job by job where I'll be able to give you an answer on that.
Awesome. Spencer, thank you so much. We are out of time now. We do have several questions that came in, but they'll be included in the Q&A report for you.
Okay, sounds good. All right, thanks everyone for attending.
Thank you so much.
Bye. Bye-bye.
All right, everyone, there is a session code, which was also available for you in the general chat, 139992. 139992 is your session code. And we are at 12:05 right now, and we're going to review the session code process. And for those of you who posted in the Q&A, posted in the general chat, please repost your questions in the Q&A so they can be included in the Q&A report for Spencer. And all the speakers will receive the Q&A report and respond to your questions offline. All right, so for those of you who are new to the process of the session code, let's go over that now. There's the first session code, 139992. And there are two ways for you to access your ATS account. The first is through the ATS website at atsseminar.com. And the second is via the ATS mobile app, which you can use the QR code on the screen to download the app and submit your session codes there. And if you go to your account on the website, please open up a separate browser window. If you are joining us from zoom.us, please go to atsseminar.com. It's a place where you registered for today's seminar. And log in using your email address and your password. Again, the same information you used or received when you registered for today's event. And if you get to the website and it says My Account, that means that you're already logged in. Just click the red My Account button and that will take you to today's agenda. And on the screen, you'll see the words Enter Session Code next to each course in today's schedule. And since we've just finished the first course, Polyethylene Sustainable Plastic for Exterior Acoustics, you're going to click on that dark blue Enter Session Code button there. And I'll take you to the session code box. And in the blank entry field, you enter that 139992. And then you click on that dark blue circle. That looks like a play button. And that will take you to the course survey. So here it is, right? The course survey, you have 6 multiple choice questions and 1 open-ended question for presenter feedback. You do need to provide feedback in order for your session code to process. Very important. And Spencer just mentioned that he does offer samples. So you'll have an additional question in the course survey. In that additional question, that is where you can request your samples from Spencer. And once you're done, hit the Confirm My Presence button, and that will take you right back to the agenda for the day. And if everything was entered correctly, you should see presence confirmed, and that's it. And if you have any questions, please be sure to reach out using the Q&A. Please do not use the webinar chat. Please use the Q&A. And handouts from today's speakers are also available for download from your ATS account dashboard. Can you please type the code? I did type it several times in the webinar chat, but I'm going to type it again, 139992. There you have it, 139992. All right. Again, and if you need help, please use the Q&A. Please do not use the webinar chat. And at this time, we are up for our next session with Steve Gleason and Chuck McPherson with Homo Sot. Gentlemen, hello, how are you?
Hello, Fulgens, and hello, everybody.
Good.
How you doing?
One moment, let me just bring you up here, Steve.
There we go.
There you are.
I won't stay up. I'll just have for a moment.
I got you.
Yep.
I got you.
Nice to see everybody.
Good to see you all. Good to see you all. So gentlemen, whenever you're ready, please go ahead and set up that screen share. And I will go ahead and post your info in the chat for the audience.
All right.
Awesome. And you're all set. Take it away.
All right. Well, thank you. Hey, welcome everybody. I appreciate y'all's attention today. And this is what we're going to go over. Designing for sound control, effective green principles and practices. And let's just go ahead and jump right into our presentation. So here's the course description. It's pretty easy. We're going to talk about designing around sound for wall and floor ceiling assemblies. We'll discuss some building codes, guidelines, and we're going to talk about strategies to meet these requirements using cellulosic fiberboard. And by the end of the course, we'll be able to specify optimal sound control strategies that fit your projects. Here's our objectives. No need to go over all those, but that's what we're going to do. And let's go ahead and jump right into the introduction. So, managing sound. Well, sound management takes all practical steps to ensure that the design process takes into consideration the protection of human health and well-being against the adverse effect of uncontrolled noise. Well, that sounds pretty ominous, but what are we really talking about, We're kind of talking about, sound and noise. And people ask a lot of times, well, what's the difference in noise and sound? Well, I think it's kind of self-explanatory, but noise is really just sound we don't want to hear. Our neighbor may think it's the greatest music ever composed, but if you don't like it and are forced to hear it because he plays it so loud, then it's just noise on your side, right? There's two types of sound management. The first type, and it's the type that we'll spend the majority of this presentation talking about, is sound attenuation. And what we're talking about there is how can we put up assemblies that will block sound and keep it in the space that it was created and stop that sound from going to other spaces, right? And we can increase the sound transmission loss between spaces in a number of ways. Three big ones are going to be damped mass, decoupling, and absorption. And we're going to go into all of these in a lot more detail. Just know the sound attenuation through these assemblies is measured two ways. It's measured with STC, the sound transmission class, and IIC, which is the impact insulation class. And we'll talk about that again as we go forward. But also know there's another type of sound management, and that's really acoustical improvement. And what we're talking about here is how the sound generated in a space sound within that space. So when you're speaking in a room, does it sound like you're speaking in a theater? Or does it sound like you're talking in your old middle school gymnasium where it just bounces around and sounds terrible? And you can improve the interior acoustics with absorption, diffusion, and scattering. And this type of sound improvement is measured on a different scale. It's measured through NRC, which is noise reduction coefficient. We'll touch on that a little bit through this presentation, but the majority of our presentation is going to be around sound attenuation. How do we keep sound in the space that it was created? At this time, I'm going to introduce Steve Gleason, and he's going to come in and talk a little bit about this slide.
Thanks, Chuck. Yes, I will be stepping in from time to time to take us on a bit of a deeper dive into some of the dynamics of sound control. The first thing I want to introduce you to is something called the noise floor. The noise floor of adjoining spaces is definitely going to determine your sound control measures. How does one room relate to the other? And of course, to know that, you're going to want to know about decibels, because you can put a decibel meter on your phone and figure out what's going on in spaces if you're doing retrofit type stuff. And you can see in our handy decibel thermometer, you've got the threshold of hearing way down at 0 and the threshold of pain, that plugged in electric guitar maybe. We're going to be dealing mostly in the scale of 40 to 60-ish hertz. That's the level of decibels that we're going to be talking about a lot. Keep in mind, though, about noise floor, there's always a noise floor in any room that you're in. If I shut everything off in here and put on my decibel meter, I'd still be getting 20 or 30 decibels of just background sound. And that also brings us to something called sound masking. Sometimes that noise floor can be problematic in a restaurant. It's called the cafe effect or the restaurant effect, where you can't hear your co-star across the table from you because of the sound around you. And you can introduce a human voice-like sound into that frequency-specific type sound that masks that. And that happens in office spaces. It happens in cafes. Chuck?
Thanks. Okay, so there are some basic applied principles for walls and floors. And the three biggest dynamics for optimal sound attenuation are: we want to decouple this assembly, we want to have mass in the assembly, and preferably a damped mass, and we want to have absorption within this assembly. And when we're talking about absorption in these type assemblies, we're really referring to insulation in the cavities of these assemblies. There's also some other things that happen within these assemblies that mass air mass, cavity resonance, and coincidence. And we're going to go over all of these as we kind of talk about how we can help control some sound. So let's talk about the codes that's driving sound control and the levels that we're trying to get at. Well, here's the big one. It's the International Building Code, the IBC 1206. And here's what the IBC 1206 says for sound. So for airborne sound, that's me talking, television on, sound traveling through the air, walls, partitions, and floor ceiling assemblies separating dwelling units and sleeping units from each other or from public or service areas shall have a sound transmission class, known as STC, of not less than 50. So what are we saying here? Again, in a building, if an assembly, whether it's a wall or a floor ceiling assembly, separates the dwellings from each other, and the IBC considers a dwelling any place you spend the night. So this gets into hospital rooms and hotels, as well as obviously apartments and condos and things like that. If that assembly is separating the units from each other, or the unit from a public area, whether that be like the hallway or a waiting room or anything like that, that assembly needs to have been tested and have a rating STC 50 or better. Also know it can be field tested, and 45 or better will work with the field test. Then there's also the structural borne sound. And what it says for that is if the floor ceiling assembly is the thing that is separating the units from each other, or the unit again from a public or service area, it shall have an impact insulation class, IIC, of no less than 50. So for the floor ceiling assemblies in these type units that are separating them from each other or from a common area, it must have an STC of 50 and an IIC of 50 or better. And again, the IIC for the floor ceiling can be field tested at 45 or better. No, there's also an international residence code that has sound in it. And for this, we're talking mostly about two-family housing, duplexes, things like that. And what it says is for the airborne sound insulation class and for airborne sound insulation for wall and floor ceiling assemblies shall have a sound transmission class of 45 or better. And again, if it's the floor ceiling assembly that's separating the two units, it must have an STC of 45 or better, and an IIC of 45 or better. So, sound transmission class rating. Well, what is that? We just kind of threw that out there, STC rating. Well, the STC rating assesses a material or assembly's ability to resist airborne sound transfer. The STC measures the sound transmission loss in decibels. The higher the number, the better the resistance to sound. So what's that mean for us in the real world? What's that look like? So between you and I right now, I'm going to build this magic assembly, and we'll start that assembly off with an STC rating of 25. Well, with an STC rating of 25, you're going to hear me just fine because normal speech is understandable. Now, if I take it up to an STC 30, well, a lot of people say you'd still hear me because loud speech is understandable. But where did the code tell us we needed to get to? Code says you need to get to an STC 50. And what happens at STC 50? Well, loud speech is barely audible. So normal speech is not audible, and loud speech isn't even understood. It's just barely audible. And if you remember the slide Steve talked about, a normal conversation between two people exists right around 50 decibels of sound. So that's really what we're doing. We're just taking out normal speech, normal talking, things like that in that range. That's being removed. So if I start out with 50 decibels of sound, it hits an assembly with an STC 50, you hear nothing on the other side. You know, if it was 60 or 65, well, then you get 10, 15 decibels on the other side. Also very, very hard to hear. Just know that as you can see, we get to 55 and up. Now loud speech is not audible. It's very logarithmic. And the higher we're trying to get that STC rating, the more work we have to do. It's easy to go from a 25 to 30. It's a little bit of work to go from a 50 to a 55. Now Steve's going to come back in and talk about how we test to get that number.
Thanks, Chuck. STC testing and IIC testing in the next slide are very, very important. It's important to get that test data document in front of you. There's a lot of acoustical spin on the marketplace, and you can get through that by reading through the test data document. It's going to have a graph like this, but it's going to have a lot of verbiage that specifically spells out all of the components in that test. And you want to compare the design that you're working on to the components in that test. And while I'm at it, let's put a UL fire resistance document on the table in front of us as well and make sure all of those components line all up so you know what you're designing for. Let's talk about that STC test. They're going to build a sealed assembly in between two acoustically balanced rooms so no sound gets around that assembly. They're going to generate 115 decibels of full frequency sound in the source room and measure it in the receiving room and graph it in that little blue line that you see, their performance line. You'll notice that there are weak points in that line. On the low end, that's the resonance dip. On the high end, that's the coincidence dip. Those are weak points. We're going to talk about them. While we're looking at that graph, let's look at the bottom horizontal axis. That's frequencies. STC's measured 125 hertz to 4,000 hertz. The left-hand vertical axis is sound transmission loss in decibels. So you want the higher the number is, the better, right? So then they take that red reference curve, which is basically the performance curve of a brick wall. No resonance dip, no coincidence dip. And you'll understand that better when we go to those slides. They raise that until they have no more than 32 total deficiencies below it, or 8 in one frequency. That frequency is just about always 125 hertz. You'll hear me talk about that frequency a lot more. And where that line intersects with 500 hertz is your single-digit STC number. But always remember, there's a lot of information on this graph, frequency specific, that you may be designing for, low frequencies specifically. Chuck, let's go to the next slide. So IIC test is very similar as far as the dynamics go, but the big difference is that instead of being able to generate a full frequency sound, they have to use this tapping machine, which is mostly mid and high frequencies. For that reason, the left-hand vertical line measures decibels rather than sound transmission loss. So the lower the number in that way that graph goes is the better, the way the graph actually dips down. And both have to be 50 for code. And always remember that You have to have that test data document in front of you. Really make sure it lines up with the assembly that you're designing. Chuck?
Oh, great. Thanks, Steve. Also know there are some lead point considerations when we're designing around sound, building design and construction, environmental quality credits. So in healthcare, you can get 1 to 2 points for designing for speech privacy and sound isolation, things like that. Also, there's some lead points if we're building residential in a high noise area and we do things to stop the exterior noise from coming into the interior of the residential spaces and things like that. All right, let's go ahead and talk about some wall applications. So I'm going to go ahead and introduce us to what we're referring to as an unimproved wood stud wall. So what do we have here? I have 5/8 gypsum wall board on either side, R13 fiberglass insulation within the cavity. It is 2x4 wood studs, and in this case, we're going to say on 16-inch centers. That is a 1-hour firewall, by the way, too. That is basically the UL 305 right there, done as a 1-hour firewall. But for sound, it's only an STC 36. And we know if we want to use this in some type of multifamily residential building, something like that, I need an STC of 50. So what can we do with this wall? Now, Steve's going to come in and talk about a few of these things.
Yeah, thanks, Chuck. Chuck introduced us to the what I call the three-legged stool of dynamics, which are decoupling, absorption, and mass. But we're going to now, in these next few slides, introduce you to some slightly more esoteric dynamics that are equally important. The first thing we have to talk about is mass law. Mass stops sound. How does sound transmit? It transmits through vibration, basically. A 6-inch brick wall or concrete wall is not going to vibrate very well, so it's going to stop a lot of mass. If you could build with 6-inch brick walls, you'd be in STC 55 territory all the time. The problem with mass law is that in order to gain 6 extra decibels of transmission loss, you need to double the mass of the assembly. That doesn't work well if you're just using straight sheetrock on a wall because it's just mass. So we're going to have to find ways to cheat mass law. So Chuck, let's go to the next slide and we'll start working on that. So cavity resonance is a problem because once we build with cavities, we have our walls start to perform like that guitar right there. That's a very old guitar, 1933 Gibson, has really old wood and it's got a resonance like you read about. That's great for a guitar, not so great for a wall because a wall, a 2x4 wood stud wall, resonates right smack at that 125 hertz frequency, which is very troublesome. It's also a fundamental frequency of human speech. So we have to figure out ways to deal with cavity resonance. How do we do that? Chuck, let's go forward. Well, the first thing we do is we put some insulation in that cavity. The air in the cavity is already absorbing some of the sound waves by creating friction against the waves. Insulation will augment that absorption, but that only goes so far. In an STC 50 wall, that's only 4 to 6 class points, or maybe 6 to 8 sometimes. So we have to do better. And one way we can do better is unbalancing the resonance by putting cellulosic fiberboard against the studs with gypsum board over it. So now the cavity has cellulosic fiberboard facing gypsum board. Gypsum board has a very low noise reduction coefficient of 0.05, very reflective, whereas the cellulosic fiberboard is 0.55, right at that critical 125 hertz. That means that you're unbalancing, you're creating asymmetrical resonance, and that 125 hertz critical resonant frequency of that cavity goes down to the 60 to 80 hertz range. Let's go forward and talk about some more problems. This is just a typical problem, and that is physical transmission. And you understand that when you realize that sound travels at 12,000 feet per second through wood, but only at 1,200 feet per second through air. So a fully coupled assembly will obviously allow for physical transmission right through the wall. So how do we deal with that? Well, the classic way to deal with that is to use resilient channel. The resilient channel allows you to screw the gypsum board only to the channel, so you're decoupling the gypsum board screws from the wall. So that's That's one good dynamic that you're introducing. But another dynamic that people don't realize is called planar flex. And to illustrate planar flex, we'll hang a sheet from a clothesline and we'll throw a tennis ball as hard as we can at that sheet. But that sheet is like a limp mass barrier. And the ball hits the sheet and all of its energy is sheared off. And so resilient channel does that as well. The problem with resilient channel, however, is that a few screws that go through into the studs short that wall out, takes away the planar flex, takes away the decoupling. If you go to a hat channel with a sound isolation clip, you have more standoff for the screws, so that's not as problematic. But you can avoid all of that by using cellulosic fiberboard on the studs, because the cellulosic fiberboard holds the screws of the gypsum board. You only screw to that fiberboard. So you're getting planar flex because it's flexible wall. You're getting decoupling. It's the best way to deal with physical transmission. Let's look at another problem. Remember, sound transmits by vibrating, by resonance, right? So we have something called the coincidence effect that is problematic, and that's really well illustrated by these two tuning forks, where you have two tuning forks in the same key, mounted 18 inches or so apart on a table. When you strike one, the one that has not been struck will resonate. Well, in a wall assembly, each material you have has a critical resonant frequency. We'll just take 5/8 gypsum board, for instance. You can see the others there. If you have 5/8 gypsum board facing 5/8 gypsum board across that cavity, or two pieces of 5/8 gypsum board together, that critical 3600 hertz frequency gets a free ride through the wall. And what we want to do is, well, first of all, we want to avoid that coincidence dip that you see right there outlined in red, and you saw it on our STC test as well. In the next slide, we want to show you how we want to deal with this. The first way is to diminish the resonance right away, diminish the vibration, like touching that humming tuning fork with your finger. What happens? It stops humming, right? So if you use cellulosic fiberboard in intimate contact with gypsum board, what you're going to be doing is diminishing the amplitude of the transmitting sound wave before it even gets a chance to fully amplify and get into the cavity. That's one way to do it. Another way to do it is to create multiple impedance mismatches on the leading edge of that wall. By that, I mean use different materials that have different critical resonant frequencies. In this way, you're making the sound wave work a lot harder. Every time it works, it loses some of its acoustical energy. So cellulosic fiberboard in conjunction with gypsum board. And also, to illustrate that, it turns out that two pieces of 5/8 gypsum board do not perform as well as a piece of 5/8 and a piece of 3/8. So you've got less mass, but better STC because you're dealing with that critical resonant frequency and you're diminishing the resonance dip. Chuck, why don't you take us forward?
Okay, so we've been talking about wood studs, so let's look at that same wall built on metal studs. These, important to point out though, are interior drywall studs. So again, the same wall that we just looked at, but on interior drywall studs, we'll have an STC 40. So interior drywall studs do perform better than wood studs, but again, it's only the interior drywall studs. And maybe at this time, let's go ahead and break for our first question.
Will just two layers of drywall on both sides of a wood stud wall achieve code compliant sound control? Yes, no, or I don't know. And you have about 40 seconds. Gentlemen, do you want to take a question too while they're answering?
Sure.
The first absolutely. First question is from Canon. What is the source of decibel scale from private or public institution?
Well, that's a great question. It was developed years ago. IBC has a lot to do with that. I would say it came from private first and it was adopted by public. Decibel's been used for a long, long time. We did our first sound test in 1931 and it was measured in decibels. So.
Excellent. And he also has a barely audible from what distance of the wall? What if someone is putting their ear on the wall?
That's a fantastic question. You put your ear on the wall and you're picking up direct resonance from the cavity. So you put your ear on the wall and you're going to get a lot more transmission. The speakers in the receiving room are about 8 feet away from the wall. That was a fantastic question.
Awesome. Thank you. Thank you, Camden. Let's go ahead and end the poll and share the results now. We have 26% yes, 70% no, and 5% I don't know.
Well, the answer is no, because if you use 2 layers of gypsum board on the wall, you're only dealing with mass law. You're not cheating mass law. You're not doing anything with coincidence. You're not dealing with anything with damped mass. 2 layers of gypsum board is not going to reach code.
Now it ends up in mid-40s. I think you started
That's
it
right.
at 36. You added another 6 decibels.
Yep.
That's all you're doing when you double max.
Mid 40s.
Yep. All right. So let's go ahead and continue along here. As soon as I push the right button, there we go. So again, with metal stud walls, like I said, the very thin interior drywall studs, your 20-25 gauge, they do perform better. However, just remember, once you start getting into structural metal studs, your 18 gauge, 16 gauge structural studs, they perform almost identical to wood. All right. Want to talk a little bit about this, Steve?
Yeah, I'd love to. This is my favorite slide. This tells us all the things we need to know about the varying components and how they cheat mass law. And we'll start over on the left, where we have a resilient channel. And that resilient channel is providing the dynamics of decoupling and planar flex, as we spoke of. That's an STC 48 wall with RC1. There is a resilient channel on the market, RC Deluxe, that's going to get you just above code. Over on the far right, we have a wall that's deploying a constrained layer damping situation. And that's because it's got 2 thin layers of gypsum boards sandwiched by a viscoelastic layer that damps both those planes of mass. That's called constrained layer damping. It's a very powerful dynamic. And we'll be able to introduce that to you again, using a floor with the cellulosic fiberboard a little bit later. Excuse me. So that's got damped mass, but it's also got planar flex because this wall was built on 24-inch on-center studs. It got STC 52. If you built it on 16-inch on-center studs, it would be in this STC 48 range. And you can see by that those dynamics that we're using, the more esoteric dynamics, are actually very important. The assembly in the center has everything that we like. It's cellulosic fiberboard in intimate contact with gypsum board screwed only to the fiberboard. So you've got decoupling, damped mass, planar flex. You've unbalanced the cavity with gypsum board facing cellulosic fiberboard, so asymmetrical resonance. You've unbalanced the source side of that wall with the different planes with different critical resonant frequencies, so different impedance mismatches. This is an STC 53 wall, but I'll tell you what, if you built that on the 25 gauge studs that Chuck introduced you to, metal studs, and put an extra layer of gypsum board on the back for good measure, that would be an STC 58 wall, which gets you up into that rarefied air close to STC 60 with just the real estate of a 4-inch wall. Chuck, let's go to the next slide. I'll stick with this. Yeah, thanks. So again, cavity resonance is something I harp on a lot, and it's really well illustrated in this double stud wall consideration because we're talking about a lot of mass on the far left, 4 layers of gypsum board, but it's only STC 44. Well, why is that? It's because 2 of those planes of mass are in the septum of the wall, right? That little space in there now has 1-inch air gap that's resonating in the 250 hertz range or so, and that's extremely problematic, and so it drives down the performance of the wall. Go to the center assembly where you've taken one of those planes out of the septum. You have a deeper cavity. You have less mass, right? But you have better score because we're cheating mass law. And that's resonating down at around 100 hertz. And then to the far right, where you have just planes only on the outside of the wall, no planes in the septum of the wall, as it should be, if you can, and we'll talk about that. That 9-inch cavity is resonating very low as far as cavity resonance, which kills a lot of tests. So this is the way to do it. But maybe, Chuck, you could jump in and talk about how a shear wall could get in trouble here.
Well, yeah, that's all I was going to say is, we've looked at a lot of these things, done this presentation oftentimes, and people always look at that double leaf assembly there on the right side and say, oh yeah, anytime we're doing a double stud wall, we always do it that way. Well, I've got many plans here on my desk that are showing the double stud wall like that is also operating as a shear wall. And they'll put the shear plane right there in the septum of the wall in the middle. I know there are some times when we kind of have to do it that way, but if we don't, we'd always like you to put that shear plane on one of the outsides, covered up with gypsum board. They do it all the time. It looks great. But if that's impossible, and we do need to put the shear plane in the septum of the wall, there still are some things that we can do to try to get the sound rating of this double stud wall back up to where we wanted it. So obviously we wanted a good sounding wall, or we wouldn't be doing a double stud wall. So again, try to avoid putting it in the septum, but if we can't, use a cellulosic fiberboard opposite the shear plane to minimize that cavity residence within this double stud wall. Now, let's go ahead and talk about flanking sound. If anyone ever talks to you about sound attenuation and how assemblies can stop sound, you have to talk about flanking sound. And what are we referring to when we're talking about flanking sound? That's sound's ability to pass over, around, and through any opening within this assembly. So let's illustrate that. We'll go back to the magic assembly that's built between you and I. And that assembly is going to start out with an STC 50. But then I'm going to put just a 1/16 inch opening in the bottom of that assembly. Well, that effectively reduces this assembly now to an STC 32, just because of the amount of sound that's going to go through that small opening at the bottom of the assembly. Well, that's interesting, but what does that really mean for us? Well, it just means that we know as soon as we build these assemblies, the next thing we have to do is come back and punch some holes in. We need certain things, you know, doors and windows, obviously, but you also need light switches, things like that. So what can we do? Well, if it's something like a light switch, recessed lighting, outlets, things like that, where we're just punching a hole in one side of the assembly, you want to come back with these putty packs and wrap that outlet or switch on the back side, kind of seal back up that one side of the assembly again. We also want to make sure that we float all of our wall edges and seal them with acoustical sealant. And that's what we're referring to. We don't want the walls to come in contact with each other in the corners. We leave about a 1/4 inch gap in there, backer rod, acoustical sealant, finish the wall out. Nobody knows that it's done that way. Also, where the wall would reach the floor or reach the hard ceiling, leave that gap, put acoustical sealant in it. Really two big reasons for this. One is as soon as we're done with the building, we know it's going to settle. And if we didn't build it this way, we'd end up with cracks and openings. They don't look good, plus sound's going to roll right through it. And it also keeps sound from, when it resonates one plane in a room, not transferring to all the planes in the room and then making its way out. Creatively route your ductwork. Obviously, if it's a straight shot of ductwork from one room to the next, the sound will just travel through the ducts that way. And you want to make sure you fit your doors well with side seals and tight sweeps. I know you're aware of STC, sound rated doors and things like that on the market, and you can specify those. But if then you hang them with large gaps around the edges and on the bottom, well, the sound's just going through the gaps. So make sure you try to seal your doors up as tight as you can. Know the door is going to be a weak point in your assembly, but if we can do some things like, seal it up, it'll be better. And again, specify acoustical sealant. If this is an assembly that we're concerned about for sound, make sure you're specifying that when they're done, they're coming back in with acoustical sealant around the switches and all that kind of stuff. Just like you specify fire caulk when we're talking about a firewall. Also know that if this is a dual purpose wall with a fire rating on it, you have fire caulk going in, the fire caulk works as an acoustical caulk also. All right, now separation walls. What we're just really talking about here is it's really good to know the type of sound you believe is going to get generated out of these areas because it's much easier to control sound between two rooms that have a similar noise floor, whether they're both loud or they're both quiet. It just becomes difficult for an assembly to control sound when you have a really quiet space next to a really loud space. That's a lot of work for that assembly to do. Let's talk about some project applications that we see out there in the real world where we've really seen some sound difficulties, let's put it that way. And one of the big ones we see a lot in multifamily construction or things like that are our corridor walls in these buildings. Well, why this becomes a difficult wall is because, it's a corridor wall. We'd like to keep it oftentimes as a single stud wall. A lot of times this wall is also going to be a shear plane wall. So we're going to have that added, shear plane in there. And some things just don't work as well that are used out there in the market. Like say using resilient channel. Well, if you put resilient channel on a wall, you can't come back and hang things or attach anything to that wall with the resilient channel in it. Because, if we go and hang cabinets or things like that, like we see in that one illustration there, that would short out your resilient channel. So that just doesn't work really well. What we're showing there in the middle is where somebody's taking a shear plane wall, and now they go, oh my goodness, I'm concerned about sound in this wall. Well, I'll just put resilient channel on it. Please never do that. You've actually created a worse problem because now we've created a very small gap that's going to resonate at a very troublesome high frequency in there and actually going to amplify some sound that travels through this wall. So here's the way we think we should be doing corridor walls and things like that with a shear plane. Go ahead, build your wall, have the shear plane on one side. On the opposite side of that wall, use a cellulosic fiberboard. Now you cover both the shear plane and the cellulosic fiberboard up with the gypsum. We can attach anything we need to this wall. It's not going to short anything out or do anything like that. And constructing it this way, we know we're going to have a minimum STC 53 for this wall going forward. This is what another project application. The slide says home office because, wasn't that long ago, it seemed like all of us were needing home offices. But what we're really talking about is what do we do if we have an existing wall and now we're concerned about sound and making it a code compliant sound rated wall? Well, we don't think you should tear the existing wall down and start over or anything. We say just come in with a cellulosic fiberboard, attach it to your existing walls attached into the studs, then come back on top of that with another layer of gypsum board that you, again, now missing the studs, attaching it only to the cellulosic fiberboard, finish the wall out. Nobody's going to know that anything was done in that. And even if that cavity is not insulated, we're going to have a minimum STC 50 for this existing wall like that. And it was a lot easier, less work and time to get going that way. Okay, let's go ahead and discuss some floor assemblies now. We've been talking about walls, let's talk about floors. Well, here's our unimproved floor assembly that we're going to start out with. So we have the 3/4 inch subfloor, OSB plywood on top. It's I-joist or dimensional lumber. And then I have 5/8 gypsum ceiling board attached to the bottom of those. Well, if I constructed my floor assembly that way, I'm going to have an STC rating of 37. And remember, in a floor ceiling assembly, I also have to have an IIC rating of about 32. So what can we do to fix that? Well, there's a lot of different things we can do to floors, but here's the one that most people are doing for floor improvements, and that's adding mass to the floor, right? If you increase the mass of the secondary subfloor, you will increase its STC rating. But important, only the STC rating by adding mass on the top. And one of the most common ways that this is done is being illustrated here. And this is poured gypsum, lightweight liquid gypsum, often commonly referred to as gypcrete. This is exactly how it's put into a building. It's pumped up there. It's poured out on the floor once the building's dried in with your gypsum up and all that kind of stuff. And doing this way will increase the STC, but the STC only. And we got to get the IIC up. So in order to do that with Gypcrete, you have to add a sound mat to it. And that's an entangled mesh, or a rubber composite mat that goes down attached to the subfloor. Then you pour the Gypcrete on top of it. It will decouple the Gypcrete from the subfloor, and then that'll also increase your IIC rating. However, there's kind of a better way, in my opinion, to add damped mass to a floor ceiling assembly, and that's a cellulosic fiberboard. So again, goes in at the exact same time you do Gypcrete, and it is glued and screwed directly to the subfloor on top. Then you put the finished floor over the top of it. This will improve the STC rating of the subfloor, of the floor assembly, and also the IIC rating. Because cellulosic fiberboard will degrade the impact sound wave as soon as the floor is hit, stepped on, walked on, and stop it from transferring through the floor. It's a much lighter product than Gypcrete. It's only about 1.2 pounds a square foot. There's actually no moisture added into the building, and it's a very convenient installation. We'll go over a little bit more of that here in the future. So here we go. We're just talking about what the IIC rating in these floors does, with the different things. Because the IIC rating in a floor ceiling assembly oftentimes is the more difficult of the two sound ratings to get. So if we did nothing, we had no underlayment at all, and we were trying to go with a wood floor or a vinyl floor, well, we're not going to make code. Look, we go to carpet and we made code. Just as an aside, that's one of the things that's really driven some of this business on floors, especially over the last few years, is now no one really wants carpet in their multifamily residential buildings. They want a hard surface floor. So what can we do? Well, you can use that poured gypsum, but you have to have it with a sound mat, and that'll get you to code. But so would just a 1/2-inch cellulosic fiberboard on top. It's going to get you to code and even perform better oftentimes than the poured gypsum does. So here we go. We live in the real world. Let's look at some cost considerations and some real practical considerations between using a 1/2-inch cellulosic fiberboard and a 1-inch Gypcrete with sound mat. Because if we're going to compare the two, you always have to include the sound mat with the Gypcrete. Well, weight is a big one. The cellulosic fiberboard is going to weigh 1.2 pounds a square foot. 1-inch gypsum is 10 to 13 pounds a square foot. So just think about it. Out of a 1,000 square foot apartment, we removed a mid-sized car out of every one of these apartments. It ends up being a significant amount of weight throughout the building. It allows your engineers and things like that to do some different designs, really help you with your overall building design. But here's the one that I see really driving a lot of this. It's the water requirement. Using cellulosic fiberboards on your floor like that, it adds no water whatsoever to the building. If you're going to use Gypcrete in these buildings, you're going to put 160 gallons of water into the building for every 1,000 square feet you pour. And just think, when does this go in? It goes in when the building's dried in. So we have the windows in, the doors in, the roofs on it. The building's been wrapped at least twice because we're very worried about water intrusion into our buildings. But now we turn around and we pour all this water into the building. Well, then they will open a window and walk away and wait for the floor to dry. Well, where did all that water go? It doesn't all magically fly out the window. A lot of it's now in your insulation. It's in your gypsum wallboard. It's in your gypsum ceiling boards. It goes all throughout the building and can lead to mold, mildew down the road. A lot of stuff like that. Installed cost, the cellulosic fiberboard is less to install than Gypcrete with sound mat. And anybody can install it. It's a very easy install. And again, scheduling requirements. As soon as the cellulosic fiberboard is down on the floor, you're back walking on it, you're using the building. With Gypcrete, we got to wait at least a week for it to dry. And because it's a third-party specialty contractor that comes on site just to do the Gypcrete, that also creates scheduling issues.
Chuck, let's go back that slide. Yeah, there you go.
Yeah.
And Fulgens, you can launch a question.
Yeah.
Of course. And what does the type of joist affect sound transmission loss in floor assemblies? Yes or no? And gentlemen, can we take a few more questions?
Absolutely.
Sure.
Next question is STC testing ASTM?
It is. ASTM. Well, no, ASTM is more structural. STC is IBC code section 1206. ASTM handles things like tensile strength and structural components, physical characteristics.
Excellent. Is there a code or guide for STC ratings between dueling units and commercial spaces?
Well, there are some codes. LEED actually gives some credit for working between spaces, but all STC is between dueling spaces, if you will. And that's what the STC IBC 1206 stipulates, between dwelling units, sleeping units, living room units, which are dueling spaces. You have to be STC 50.
Excellent. And what about STC rating for non-dueling spaces, in particular classrooms?
Well, classrooms don't have a specific rating because they're not they're not living units and they're not sleeping units. But usually you use STC 50 as bottom line. Classrooms really like to look, as with hospitals, like to look at STC 55.
Excellent.
Yeah, they'll usually just be putting the guidelines of the plans and stuff.
Right. So more of a guideline than a code.
Awesome. Thank you. And let's go ahead and end the poll and share the results. So we have 79% yes.
All right. And that 79% is correct.
Yeah, go right to that slide and you can, there we go.
So as you can see, an open web joist does perform slightly better for sound than I joist or dimensional lumber. It's not a huge amount, 1 to 3 decibels, but the I joists do perform slightly better than like I said, the dimensional lumber. I'm sorry, the open web does than the dimensional lumber or the I joist. Just one other thing when you're talking about joists, just know when you move across the floor, it may emit a low frequency, like moaning sound, because the whole assembly moves. That's not in the code. The code is referring to the sound generated from the impact on the floor. Also in our floor ceiling assemblies, there is some decoupling that's going on. And this is achieved by using resilient channel on the bottom of the joists and then hanging the gypsum ceiling board to that resilient channel. Just know that the resilient channel is in there mostly for the fire code, because by creating that space between the joists and the ceiling board, it allows that floor ceiling assembly to maintain its fire rating for the hour and a half or 2 hours, whatever that particular assembly is rated at. And it also allows your gypsum contractor to get a lot smoother ceiling by hanging it on the resilient channel that way. But it does help in the sound transmission through this assembly also. But do know that we've done an awful lot of testing in that little space there between the joists and the ceiling board. And doing a lot in that space really does not help that much for the overall sound rating of the floor ceiling assembly. We need to get on top of these floor ceiling assemblies and attack the top side in order to really improve the sound attenuation of a floor ceiling assembly. If we're trying to get higher STC and IIC sound ratings in our floor ceiling assembly, there are some additional things we can do with a cellulosic fiberboard. And one is what we refer to as our sandwich application. And it's basically the same application we've been talking about. We have the subfloor, we put the 1/2-inch cellulosic fiberboard on top, but then come back on top of that cellulosic fiberboard with another layer of 3/4 inch plywood or OSB or something like that, kind of sandwiching that cellulastic fiberboard on the top side, and we can get pretty high STC and IIC sound ratings that way. So here's an example. This is the UL 570. So that's just an 11 7/8 I-joist. But with that sandwich method on the top, that floor ceiling system tests out with an STC 58 and an IIC 58. So again, we're right around that 60 level. If I had done that same floor ceiling assembly on a 16-inch open web, well, now I am pretty close to that. I am at that STC 60, IIC 60. There's some few project applications we see a lot of use for the cellulastic fiberboard infill projects. So this is converting existing buildings into residential buildings. They're in towns usually. They're older buildings. So pumping in gypcrete and all that, concrete and mess and all that stuff is kind of difficult. Cellulastic fiberboard is going to go right up the buck hoist with all your other building materials. We're not going to add any water or weight to the building. Still going to get all the sound ratings that we need. I see a lot of use for us in infill projects and things like that. Here's a little quick product comparison. It's almost like we did this slide ourselves. Look, cellulastic fiberboard is going to get all the things that help us achieve sound attenuation in these assemblies. The other products out there maybe only hit one or two things. Also know there are some other considerations in the market. There's acoustical consultants that you can reach out to that can help you with this, and third-party testing. There's some big players in building products, and some of these guys own their own labs, do their own tests. I'm not saying they're doing anything shady. I just like it when I can see some things compared in a independent third-party lab. Also know that just putting cellulastic fiberboard in your wall as a sound barrier is also going to increase the R value of this wall. It's going to save you about 15% on your energy bills, because in addition to stopping sound, we're going to stop more thermal transfer through this wall also. And that is what a cellulastic fiberboard looks like before it is a cellulastic fiberboard. All cellulastic fiberboards are made from post-consumer paper. We take paper and take it all the way back to its original pulp slurry mix through only heat and agitation. That pulp slurry mix that looks kind of like a thin oatmeal will get poured into a form. Starts out about 16 inches thick. We extract the water and compress that pulp slurry mix together, and that is what makes a cellulastic fiberboard. There's no binders, there's no adhesives added to it. It will off-gas over time or break down over time. A cellulastic fiberboard will last the life of your building, and there's nothing toxic in it. So that's how it starts. It'll get pressed into a board, dried, cut to shape. That's how we do that. I'm gonna go ahead and move on. So again, there's lead credits when you're using cellulastic fiberboard because we're using a recycled product. And that concludes the AIA portion of this. This is what we went over. Now we have the ability to discuss the qualifications and benefits of walls and floors assemblies when designed for sound. You can review the principles of sound management as it pertains to specific types of assemblies. You can describe sound control strategies that are particular to common wall and floor ceiling assemblies. And we should be able to examine sound control design methods for walls and floors using sustainable, mold-resistant cellulastic fiberboards made from recycled materials. Any questions on this?
Excellent. Thank you so much. We do have tons of questions that came in. Let's see how much we can get within the next 10 minutes. All right. So the next question is, does cavity insulation need to be full cavity depth, or is there a minimum thickness?
It should be full cavity depth, but while that is on the table, it doesn't want to be over cavity depth. In other words, you wouldn't want to jam R19 into an R11 cavity, because then you create a physical transmission path by compressing the insulation. But yes, it should be full.
Excellent. And for those of you who want the session code 140016, it is posted in the webinar chat. The next question is cellulosic fiberboard less expensive than gypsum board?
It's a little more expensive than gypsum board, but it's a specialty product. If you use 2 layers of gypsum board to get your code, you're not going to get it. So it's a little more expensive.
What is drywall stud versus wood stud?
Well, Chuck explained that pretty well. A drywall stud is a thin gauge stud. It's like a 25 or 20 gauge stud. It's a C-shaped stud, so it gives you built-in planar flex, whereas a wood stud is obviously fully transmitting the sound as a mass.
Yeah, there's no structural characteristic to an interior drywall stud, so that's why it's an interior wall stud to begin with. And it's kind of like doing 24-inch centers as opposed to 16s or something like that. Like the wall can't support anything either. But
Excellent. Cellulosic fiberboard will attach to the stud. Does a gypsum board also attach to the stud?
No, in this case, in the homosote wall, which we're about to go into, the gypsum board attaches only to the cellulosic fiberboard. And we've tested the pull strength of a number 10 drywall screw, and it's 81.6 pounds. So that way you get your decoupling from the studs and you get your planar flex. The screws do not go into the studs.
That helps keep the screw from transmitting the sound through the wall too. Yep.
Can you retain the fire rating of the typical wood stud wall when fastening the drywall only to the cellulosic fiberboard in lieu of direct to studs?
Yes, in fact, that's a U305 wall, and if you got U305 in front of you, you would see that in system number 14E, it spells out exactly that fastening method, because that is how we burn tested that wall.
Excellent.
Sometimes the UL is going to require you to attach the perimeter of the exterior gypsum wall board to the studs, but that doesn't really affect the sound. It's still going to miss it in the bodies of the gypsum wall board.
Excellent. What is the most cost effective between channel versus fiberboard versus constrained?
Well, to be honest, a resilient channel is straight up going to be a little less expensive. The problem is that it's fraught to failure, because with resilient channel, all it takes is a few screws to go through the channel into the studs, and you've lost all of your planar flex and all of your decoupling. So you spend a little bit more for the cellulosic fiberboard, but you get foolproof sound control.
Is cellulosic fiberboard more or less dense than gypsum board? And what is cellulosic fiberboard fastening holding strength?
It's a little denser than than gypsum board due to its unique structure. And as I mentioned, its fastening strength, its pull-out strength is 81.6 pounds.
Excellent. Can you talk about the screwing into the cellulose, size, ease of non-failing insulation, holding power over time, and vibration?
Over time, it'll hold forever. If you at some point reach out to us, we'll send you a sample, and you can see that screw stays in there forever. As far as insulation, I'm not sure how we address that, but it's got holding power over time. It doesn't come apart at all, the cellulosic fiberboard, because it has no adhesive in it. Even if it gets a little damp, it still will not come apart. So
in our installation instructions, we actually wanting you to use laminating screws to attach the gypsum wallboard to the cellulosic fiberboard, and yeah, they don't separate.
No, they definitely never do.
Awesome. Removal of inner gypsum boards in multi-layer partition improves sound insulation, but in the same time, will it affect the fire rating?
No, it won't. The fire rating, the burn rating on that wall is done from the outside of the wall. 1 layer of gypsum board on the outside of that double stud wall is going to give you 1 hour fire rating. The gypsum board that goes in the middle is, people put it in there because they think that they're putting more mass in the wall, and that's the place to put it. But the fire rating is established from that single layer of gypsum board on the outside of the wall.
Doesn't decoupling a self-leveling floor from the structural deck defeat the product warranty?
I can't address their product warranty, but they always have to decouple. All of their sound tests, all of their documentation is built on the mass of the poured gypsum and the decoupling of the sound mat. So I would have to say that their warranty probably covers that.
Excellent. We'll perhaps take one or two more. For doors, what is the best solution for the bottom of the door?
Well, Chuck addressed that beautifully. You have to make sure you have a state-of-the-art seal at the bottom of that door. Remember that little opening at the bottom of the door is going to kill the sound test on that door assembly.
Excellent. And last question. For doors, are common weatherproofing or common weather stripping accessories like neoprene built at jamb and head, are these effective for sound attenuation?
Yes, I would say they are. We don't specialize in doors, but I would say they are. As long as you're blocking that opening, as long as you're not letting, as long as you can't shine a light through it, then you're going to be defeating flanking sound.
Gentlemen, excellent presentation. Tons of other questions, but they'll be available for you in the Q&A report.
Thanks for the questions, folks.
Thank you. All right, everyone, there is the session code for you all on the screen, 140016. 140016, another excellent presentation with Homosot. 140016 is your session code. If you have any additional questions, please use the Q&A, and they will be marked for Chuck and Steve for the Q&A report. So please, you still have time if you want to submit any of that. And let me go ahead and
thank you, Fulgence.
Thank you, Steve. Thank you, Chuck, as always. All right, at this time, we're going into our break from 1:10 to 1:30, and we will be back with a word from our sponsor. So we'll see you at 1:30. I'll keep the session code up on the screen in the meantime while I label your questions for the Q&A report for Chuck and Steve. Enjoy your break and see you soon. Hi, Nina. I see that you're signed in twice. So can you just unmute so I can know which one?
Yes, I'm on this one. I'm not quite sure where the other one is.
Okay. Okay, I got it now, but thank you. All set.
Okay, cool.
Hello, everyone. Fulgence here with ATS, and this week we're featuring a very popular on-demand course, Prefabricated Fireproof Columns, presented by Trish Brindle of Firetroll. You'll get a quick look at the difference between active and passive fire protection, see how prefabricated fireproof columns stack up against other options, and pick up a few key design tips along the way. And here's something exciting. Trish will be joining Jen and I live right here on LinkedIn next week, Friday at 2:30 p.m. Eastern, for our next episode of Built for This, where we'll dive deeper into how Firetroll's innovative fire-rated solutions are helping design professionals address compliance, performance, and aesthetics all at once. So check out the on-demand course now on atsseminar.com, and we'll see you live next week right here on LinkedIn. Hello, everyone, and we are back from break. And at this time, I'd like to introduce you all to Nina Tuzova with Iconi, our sponsor for today. Nina, hello, how are you? Nina, can you hear
I'm
us?
doing great.
Okay.
Thank you so much. Let me get my screen shared.
Absolutely.
Yep. Can you hear me?
Oh, yes, we can hear
Okay,
you now.
awesome.
Yes.
Well, off we go. Thank you. Awesome. Off we go. Thanks everybody for joining. Welcome back from your break. My name's Nina Tusova. I am the Regional Sales and Marketing Director at Iconi, based in the Southeast region, and I'm very excited to share our materials with you. For those of you that don't know Iconi, we specialize in materials for high-end modern interiors. We're known for unique, high-quality finishes for made-to-order cabinetry and panels for walls, ceilings, and so much more. So the company itself, we're based in New York, but our materials, they're sourced from all around the globe. So we're bringing very high-quality materials to the US. So as you can see, materials that we have, they're ranging from unique metal finishes, decorative metals, woods, flexible woods, and so much more. We have about 15 different material collections, all of which can be used for various interior surfaces. But for today, we're going to be focusing on our acoustic collection just to stick on the theme of the day. So here you're seeing the 4 main players of our acoustic collection series. So something we always strive to do at AAPEI is to create very high functioning materials while also uniting them with beauty and design. So as you see with across our 4 acoustic products, they're not really your cookie cutter acoustic panels. They don't look like the typical fabrics and meshes. They look a lot more like decorative panels. That's exactly what we aim to do. So across all of these products that we'll dive into in a little bit, they are all boasting a pretty great NRC rating of sound absorption between a 0.8 and a 0.95. And any of them can actually be ordered with your choice of a real natural wood veneer finish, a melamine wood finish, or a lacquer of your choice of color. Jumping into our very most popular acoustic panel, it's the AAPEI Sound. So you can see here, it's actually popular for its ability to be curved and flexed, as you see in the bottom left ceiling photo, which is a very unique thing with these types of acoustic panels, as I'm sure you're very familiar. And it can also be used for flat surfaces as well. This one comes in at an NRC rating of a 0.8 on walls and a 0.85 on ceilings. Very classic, traditional, and timeless, I would say. Then our AAPEI Sound product actually has a subproduct of the PF402, which is really just the code for this version of it, where the lines on the front-facing layer are a lot more sleek and minimal for a much more subtle modern design. It's available in various sizes you can see on the screen. But at AAPEI, we don't like to say no. We always want to come alongside of designers and collaborate with them, partner with them to bring their vision to life. So we do have other sizes available as well. All of our acoustic products, they do follow this 4-layer system, which is actually what allows them to be not only beautiful, but also amazing on the sound absorption that they provide. So the top layer of the finish, that's going to be always up to you and your visual preference. You can choose like the wood veneers, any color you want. That's going to be the beauty aspect of it. But behind that, what's going on is we have the MDF layer. That's the first layer of absorbing sound. It has perforations in it. And then we have another perforated layer, the compensation facing behind that. And then we have the standard non-woven fabric layer on the back, which is very different than usual. Usually there are just about 1 to several layers on these acoustic products when they are just the fabric. So that's something that's really differentiating these materials and letting them absorb that sound. Then our next product, the AAPEI Shape, it's covered in these micro perforations like you can see, but from afar, you actually will see more of a flat surface. You won't see these micro perforations as much. This one is available also with this wood slatted appearance on the, like you see in the image on the bottom left. So we can cover it with wood slats. So it's a very hidden acoustic feature in your space. This one is actually the highest NRC rating that we have, coming in at a 0.9. Still following that same 4-layer structure that you can see on the bottom right, and available in the different colors and finishes of your choice. Next up is the AAPEI Barcode. This one is actually one of my personal favorites. I think it's just so unique, very modern still, and just beautiful. In this project, I love how it was mixed with both a wood veneer and then a lacquer color as well to continue that design while adding some different dimension and color to it. So This one's available in a very large size of 9 feet by 5 feet. So that's going to be great for ceiling installs and walls. But again, available in other sizes as well, just like all of this collection is, and various thicknesses too. So also something that I love to note, all of our acoustic products, they can be installed in existing ceiling grid systems. So you don't necessarily need to change out the whole grid. You can just slide these in and use the previous grid. But we also do have a grid system that allows ceilings to hide the grid, like you see in this project here. You don't see the grid system at all. It's a hidden version of it. And so the design gets to continue to be seamless with these lines going across the ceiling without any interruption. The NRC rating on the Iconi barcode is a 0.85. So just amazing sound absorption. I love to include these images to really show how it can also be used on furniture. So these drawer fronts are also absorbing sound, and it can be used in just really any interior surface. Here are some of the finishes that you can select from between lacquer colors, the naturally wood sliced veneers, and then the melamines to look like wood, which is a more cost-effective approach as well. But we do like to have all the different options for you to select from. And we are at Iconi very proud that all of our wood materials that you see, not just in the acoustic collection, but across all of our collections, they are FSC certified, so sustainably sourced. And we really do not have time for all of our materials, but I wanted to share with you just a few more of our favorites here. You can see the sculpted liquid metal, the woods, dimensional woods, and metals as well. And so really we have about 15 material collections, and we really do believe that the beauty of design is in mixing various textures and materials within a space. And so I like to say that we are a designer's one-stop shop for surfacing finishes, because you can come to Iconi and find cement, clay, metals, and just so many different elemental materials that really blend well together in a space, and can also be ordered as made to order cabinets, furniture pieces, and so much more. So we really pride ourselves on working with you to make your vision come to life. And so I'm just, for the sake of time, going to stop there so we can do the poll question and see if you guys have any questions for me. I'd be happy to answer them.
Nina, thank you. That looks amazing, and the people in the chat agree. It looks gorgeous. So let's go ahead and launch that poll question for you all. And if you have any questions for Nina, please use the Q&A. And there is the poll. Would you like to receive a few samples of our wood or acoustic panels? I don't know who's going to say no to that. So go ahead. You have 1 minute to reply.
And I'll be following up with you all about that after this.
We'll just give about 10 more seconds. Oh, we do have a few questions coming in while they're working on that poll. Michael asks, are these for residential and commercial?
Yes, all of our materials are used in both spaces.
Excellent.
And the acoustics are rated for commercial as well.
Excellent. Lizette asks, do you have a Canadian distributor?
We do. We can connect you.
Excellent.
You can email info@Iconi and we will work with you.
And Christina asks, which is the most economical product?
Economical in what sense? I just want to make sure.
Christina, can you please clarify? And Bruno is asking, great product. Are there any panels for exterior applications?
Great question. Most of them are only for interior, but we do have a collection. It's our decorative metal collection. When you go to our website, that one is used for exterior. It's actually a very unique collection of 100% pure metal with unique designs that you can get into it, where we actually create those designs using a controlled oxidation process. So it's just perfect for exterior and can still be used interior as well.
Excellent. Christina, follow up by saying cost. That's what you meant by most economical.
Oh, the most economical, I will say the most cost effective is our textured wood collection. And across, honestly, most of our wood collections and a few specialty materials as well, there is an option that, it ranges a lot. So we can always work with you to find one that's on the more economical end and kind of find some in that tier. But I would say the textured wood, some of our flexible and milled woods as well, and our embossed wood veneers are the more economical.
Awesome. And Rachel's asking, can any of the panels be custom finish matched to existing finishes in a historic building?
In a historic building, we've done this before. It really depends on the project and how much we're producing of it. We would love to work with you and make a custom match for you on the woods. But then as far as the other materials, we can 100% do a custom match, like with our cements and clays, lacquers, and materials like that. It's very, very easy for us to do a custom match. But we do, with our wood collections, have about 10 different wood finishes as well.
Excellent. And we have one more question regarding how much is the price range?
So with the acoustics, it's starting at about $30 a square foot, ranging up to $85 a square foot. That is dependent on a lot of different factors. And across the other material collections, we can share price lists with you after, since every material is very different.
Excellent. And let's go ahead and end this poll now and share the results. So Nina, we do have several folks saying, yes, please send samples, 52 folks, and about over 20 folks asking maybe please send some more info first.
Happy to do so.
Excellent.
Awesome.
Nina, thank you so much. That was awesome.
Awesome. Thank you, guys. My pleasure sharing with you all today. And I will connect with most of you soon.
Thank you.
Thank you. Have a good one.
You too. All right, everyone, there is your sponsor code. It's 147456. You can enter that also in your ATS dashboard along with all of your session codes. 147456 is your sponsor code. And I'm going to add that in the chat for you all as well. One more time, 147456. There you go. All right. And we are moving along with our agenda, and we have our next course, which is acoustic door assemblies and their role in sound control. So please join me in welcoming from AMBICO, Steve Peterman. Steve, hello, how are you?
Good afternoon, everyone. Good afternoon, Fulgens. I'm great, thanks for asking.
Awesome. Good afternoon.
You can hear me fine?
Yes, hear you great.
Okay.
Look
Awesome.
great. And whenever you're ready, go ahead and share that screen so we can get you all set up here.
Okay, so let me figure that out. So are you seeing the presentation screen at the moment?
No,
Oh,
right now it's just
there
us
we
on
go.
camera.
There we go. How about now?
It's coming up soon. And just go ahead and make that full screen for us.
Right.
Perfect. You are all set, my friend.
Okay. Awesome. Well, thank you. So thank you, everybody, for sharing your time with me today. My name is Steve Peterman, and I'm with AMBICO Limited. I'm VP of Business Development with AMBICO, and I'm here today to talk to you about acoustic door assemblies and their role in sound control. So I know that this is very sound, acoustic and sound focused. So I think I'm number 3 presenter today for you. So hopefully this is helpful for everyone and you find it useful information. This course is approved by AIA and is good for 1 HSW credit. It is also approved by the GBC for their course as well. All right, so let's get into what the course description is, and then we'll talk about some learning objectives. So sound control is a critical element to a building design. Let me move this. How an occupant will use the space must be understood in order to deliver a healthy and functional environment free of noise. Is speech privacy important? Is this a learning environment? Does the office open to a manufacturing floor? Well, we all think of walls, ceiling, and floors when discussing sound attenuation, but we must not overlook the importance of an acoustic door assembly. Without the proper acoustic door, the sound control goals in an acoustic plan may not be met. So this course will review healthy sound levels and how to test and identify target STC ratings. We'll discuss the elements of the acoustic door assembly and how the assembly addresses fire ratings and ADA compliance, how it contributes to LEED certification and green building, and provides security for classified files and electronic data. So at the end of this course, all participants will be able to recognize the importance of proper acoustic control relative to requirements in WELL V2, LEE V4, BD plus C, and ID plus C rating systems, health, speech privacy, security, and the ability to learn. We'll explain how to use key sound measurements in determining a successful acoustic plan with a focus on acoustic door and frame assemblies in environments such as schools, offices, theaters, and medical buildings. We'll describe the door assembly, its role in WELL V2 and LEE V4, BD plus C, and ID plus C rating systems, and the importance of specifying the entire door assembly from a manufacturer who offers test reports from an independent and certified lab. And finally, we'll discuss the performance options available in acoustic door assemblies, including the level of sound control, fire ratings, ADA compliance, security, and contribution to LEED V4, BD plus C, and ID plus C rating systems. All right. So let's begin with establishing the importance of acoustic control in the built environment. Acoustic control is a vital consideration in health, safety, and welfare of building occupants. Sound transmission control, also referred to as sound attenuation, should be addressed with the design of any building. Acoustic control must be addressed with consideration of the proper level and quality of sound to utilize the space as planned. So, for example, schools, theaters, corporate offices, medical buildings, military facilities, SCIFs, interrogation rooms, labs, and testing facilities. Well, consider that the health impact on office staff, speech privacy in a medical exam room, the ability to learn in a classroom or communicate effectively in a boardroom or meeting room, and protection of sensitive electronic information all has to be considered in across a wide range of different applications. Acoustic control at work and school is essential. The right acoustic door is a critical element of the acoustic plan in these applications. Patient exam room or an interview room in a medical building facilitates private conversations that should not be heard outside that room. The noise of a concert hall, a machine room, a testing facility, or a laboratory should be contained to those areas. And sensitive classified information and electronic data and communications should never be breached. Well, since March of 2020, we're all spending a lot more time at home. Acoustic comfort is critical, especially in multi-residential buildings. In an acoustic plan must be considered in multifamily dwellings, assisted livings, retirement facilities, and university housing. Not only do poorly designed multifamily designs lead to angry neighbors, but constant background noise can also lead to health issues for residents. So all of this leads to, well, how loud is too loud? Living or working in spaces at lower than 40 decibels is considered safe. A London epidemiologist, Dr. Uton Samuel Kai, led a study of some 365,000 people and found that road noise affects the cardiovascular system and can increase the risk of heart attacks. Another study at the London School of Medicine found similar results with an increase in type 2 diabetes cases. The World Health Organization has calculated that at least 1 million healthy life years are lost every year in Western European countries because of environmental noise, with cardiovascular disease contributing to the vast majority of these deaths, especially high blood pressure, heart attacks, and coronary heart disease. It is thought that the noise triggers the release of the stress hormone cortisol, which damages blood vessels over time. So this brings us to our first poll question, Fulgence.
Excellent. Before today, did you know that high noise levels can contribute to health problems like heart disease? Yes or no? And we'll give you about a minute to answer. All right. Thank you for your participation in the poll. So, Steve, it's almost split, but 54% yes.
That's cool. That's kind of what I expected. Um, it's really interesting, before I started doing some research on and working on this course, um, I, and Ampico has been in the acoustic, business for over 50 years. But quite frankly, for most of that time, it wasn't really considered a health issue. It was more of a, something that we wanted to control for people's, learning capabilities or just better experience in a space without really understanding that there were truly health benefits to it. So it's interesting that that more and more people are recognizing that now. I think that's a good thing, and certainly there is growing medical evidence that controlling noise can really be beneficial to our health. So well done, everyone that knew that. All right, moving on. So, um, poor acoustic control in the workplace can lead to poor performance, increased stress, and absenteeism in employees, and not to mention concerns for privacy. The National Institute for Occupational Safety and Health, NIOSH, established a recommended exposure limit, or REL, for occupational noise exposures to be at 85 decibels, which is a weighted dBA as an 8-hour time-weighted average. Exposures at or above this level are considered hazardous. The REL is based on exposure at work 5 days per week and assumes that the individual will spend the other 16 hours in their day as well as weekends in a quieter condition. Acoustic control is critical to speech privacy in the workplace, medical practices, and hospitals, government buildings, and in military facilities. Consider background noise in a classroom setting. Well, background noise interrupts concentration, it degrades the ability to communicate, and it ultimately hampers learning. This includes noise from vehicular and air traffic, foot traffic, adjacent classroom noise, mechanical equipment, reverberation within the classroom, and specialty rooms like music, shop, cafeterias, and auditoriums. In today's medical, military, and corporate environments, there's no room for error in security. Sensitive classified information housed in a SCIF provides security when built to the ICD ICS 705 requirements. Security concerns in these applications not only include speech privacy, but include protection of electronic data through radio frequency shielding as well. So next we'll briefly discuss acoustic testing and specifying the appropriate STC rating for acoustic components based on a room's use. Designers and architects should consider three key measurements when it comes to acoustic control. The first is STC ratings, the second is background noise, and finally reverberation. So first, the STC or sound transmission class rating measures sound transmission loss in decibels through a barrier. The higher the STC rating, the greater the performance level or sound attenuation of the acoustic barrier. Sound attenuation is defined as the reduction in the intensity of sound that's transmitted from one point to another. So the standards used are ASTM E90, ASTM E336, ASTM E413, and finally ASTM E2964, all measuring sound from 125 Hz to 4,000 Hz. ASTM E90 is the standard test method for laboratory measurement of airborne sound transmission loss of building partitions and elements. So this is the standard that we would use or the lab would use when we go in to test our product in a laboratory environment. So this defines how the lab is supposed to conduct that testing. ASTM E336 is the standard test method for measurements of airborne sound attenuation between rooms and buildings and is the standard used for field testing of barriers. And then ASTM E413 is the classification for rating sound insulation. It includes the algorithm for applying the results of the transmission loss across the 16 different test frequencies, and it produces the single value STC rating for the tested assembly. And that doesn't matter whether that's the lab test assembly or the field test assembly. You take the results of those tests and you apply it through the algorithm that's included in E413, and that produces the single STC rating. Or in the case of field testing, they may report in a different way, but it still uses this standard and that algorithm. ASTM E2964 is the standard test method for measurement of normalized insertion loss of doors. So this is the test standard that's referenced in E336, but it is a newer standard that has been created primarily for testing door openings or openings of 6 meters squared or less. Accredited acoustic engineers can perform acoustic field testing as follows. First, they generate noise in one of the rooms connected by the partition. The noisy room is typically called the source room, and the quiet room is typically called the receiver room. They measure the average sound pressure, or LP, in each room and calculate the transmission loss, or TL, across the partition at set frequencies, which are 1/3 octave bands between 125 Hz and 4000 Hz. Following the ASTM E90 for rooms or lab testing, and E336 for partition or field testing, or E2964 for doors in the field, depending on whether you are in the lab, the field, and the specimen size. Test specimen size. And then finally, they calculate the single number acoustic rating by comparing the measured TL values to the standard STC curve given in ASTM E413. So to identify the proper STC rating for a project, one must first calculate how much sound reduction is required. The table on this slide provides an example of the process. The first two columns list the ambient noise levels in different working environments. The third and fourth columns list the optimal ambient noise levels. So for example, you may be designing a broadcast recording studio where the background noise cannot exceed 30 decibels. This area will be next to a classroom where television monitors will be on at all times, creating noise levels of about 80 decibels. With these two measurements, you can now estimate the approximate STC level of the acoustic door should be 50. You subtract the desired noise level of 30 from the noise created at 80, and that gives you the difference of 50. Now, this is an approximation only, since you should also consider frequencies of the source noise. Under ASTM E90 and ASTM E413, a product is given an STC rating, which is an average of its acoustic performance across different sound frequencies between 125 and 4000 Hz. The calculation is determined by the testing lab. ASTM E90 is the standard method the lab will follow to test the products, while ASTM E413 outlines the calculation needed to determine an STC rating for the product. The calculation outlined in E413 uses the results of the test outlined in E90 in order to make this determination. So here the performance of an STC56 acoustic door is measured across 16 different frequencies between 125 and 4000 Hz, indicating the extent of the noise in decibels stopped by the door at each frequency. Now, when we zoom in on this, you'll notice that the STC contour is not flat. It attenuates less sound at low range frequencies than it does at high range frequencies. And the STC contour curve is illustrated here as the dashed line in the graph, and the solid line is the test specimen as it's measured across the various frequencies. So you can see the test method, or the test specimen, is plotting points at these 1/3 octave bands across the range of test frequencies, and it goes above and below the STC contour curve. And everywhere it drops below the curve, you can see that they're showing the deficiency levels at those points where it drops below the curve. So you see 3, 6, 3, 3, 4, and so on. Those are the deficiencies on the test specimen at those frequencies. In workplace environments, the CDC recommends NIOSH Sound Meter app. Now, NIOSH is the National Institute for Occupational Safety and Health. Now, this free app provides up-to-date information informational screens on what noises are considered hazardous, how to conduct a noise measurement, how to properly select hearing protectors, and guidelines for preventing hearing loss. And it is a free app. I find it quite useful, so I threw it in here. I use it to check noise levels in different environments. I can use it to troubleshoot leaks around openings, that sort of thing. It's quite handy for that. So um, we'll send you. In fact, in our space, you can find the deck, and you can certainly get to this slide if you have interest in downloading this particular app. The most common field testing method used is ASTM E336, reporting the results as apparent sound transmission class, or ASTC, which is typically 3 to 5 points lower than the STC rating, which was performed in a lab. The ASTC rating is really considered a worst case scenario. A field test reflects flanking where sound is escaping through a partition from an element in the acoustic plan. Therefore, one element may test at STC 50 in the lab in a controlled environment, but may test at ASTC 45 in the field due to flanking and other key acoustic components that in the field are being attributed to factors in the ASTC test result. So it's really understood that when you're testing in the field, it's not optimal conditions, and you're likely going to get effects from other materials in the results. And so that's typically built into what's allowed for performance in the field compared to the lab result. The second measurement to consider is the level of background noise. So background noise is difficult to isolate and control. This could include sound from building systems, exterior sound transmission, and sound from adjacent spaces like classrooms. The Acoustical Society of America partnered with the American National Standards Institute to develop the ANSI S12.6 in recognition of the importance of designing a high quality acoustic environment for education. Acoustical performance criteria determine design requirements and guidelines for schools. This standard aims at maximizing speech understanding in learning spaces. Numerous school districts and state and local agencies have implemented this standard as part of their construction and renovation requirements for schools. The ANSI S12.6 is the guiding document in the Lead for Schools Indoor Environmental Quality IEQ Prerequisite 3 Minimal Acoustical Performance, the IEQ Credit 9 Enhanced Acoustical Performance, and the CHPS or CHIPS IEQ P9 credit. This standard states that it's the architect's responsibility to specify systems to meet the background noise standards outlined. If the noisiest 1 hour period during which learning activities takes place is dominated by transportation noise, then the maximum noise limits are raised by 5 dB. Although this standard and the LEED credit determine background noise levels based on HVAC noise, there are other sources of background noise within a classroom that can be controlled by acoustically separating the space from the source of the noise. This can be achieved through the use of storm windows or insulated glass units to limit noise from exterior, as well as specialized door and frame assemblies to limit noise transmission from interior spaces. The third key measurement is reverberation, the persistence of sound after sound is produced. After a sound has been made, the waves from that sound continue to travel. When those sound waves hit and reflect off surfaces like walls or furniture, the sound can persist even after the source of the sound has stopped. This creates a sonic effect called reverberation. When sound waves repeatedly bounce off surfaces, the clarity of the sound diminishes and becomes muddy. Think of what it's like to listen to a conversation in a crowded room. The ANSI standard also refers to both reverberation time and the STC ratings of ceilings, floors, and walls. The acoustic plan should consider how the space will be used. So, for example, restaurants or classrooms, auditoriums, and what products can be used to reduce reverberation time. And those are different applications, so the solutions can be different as well. The higher the STC rating, the better the performance. Understanding the optimal rating should be based on the use of the space along with the use of adjacent spaces. Single or composite walls, floor ceiling, and roof ceiling assemblies should provide specific STC ratings when separating a core learning space from an adjacent space. When considering sound attenuation, all building components must be taken into account when designing areas where door, frame, and window assemblies are to be provided. Increasing an STC rating is complicated. So, for example, going from a rating of 40 to 41 is much easier than going from a rating of 50 to 51. The ratings are a sliding scale, and the higher you go, the more complicated the solution. Therefore, it's important to know your sound attenuation goals before determining the STC of the door. Higher frequencies can pass through small cracks, but can be blocked by flexible and lightweight materials, whereas lower frequencies cannot fit through small cracks and require heavy and stiff materials to block them. To reduce sound transmission, carefully consider the placement of electrical outlets, so don't place them back to back. Specify on drawings for contractors to seal all joints and penetrations with an acoustic sealant. Properly designed and executed wall constructions are crucial to the performance of acoustic door and frame assemblies. A significant issue on the job site is the lack of adherence to field tolerances. Additionally, floors must be completely level at opening thresholds. Acoustic frames must be installed in complete accordance with manufacturer's installation instructions. A comprehensive acoustic plan includes walls, ceiling, floors, windows, and doors. All must work together to meet the acoustic objectives. Therefore, no one component should be overlooked. Each element may be specified and manufactured separately. So today we're going to focus on the acoustic door assembly, which leads us to our second poll question, Fulgens.
Excellent. How often do you specify an acoustic door as part of a complete acoustic door and frame assembly? A question came in. Folks, if you have any additional questions, please use the Q&A panel and not the webinar chat. The question is, we specify an STC 50 partition, but include an STC 45 door. Aren't we creating a sonic hole and rendering the assembly down to an STC 45?
So not quite. I think the way I'll answer that is if your goal, if your client's need is to generally have an acoustic barrier that performs at a specific rating, then you can combine ratings of different components. So you could have a wall that's rated at 50 and a door that's rated at 45. And the net result to the barrier is, depending on how many square feet of wall you have at 50 as compared to how many square feet of door you have at 45, gives you a net performance of the overall area of that barrier based on the components volume on that barrier area. So you can certainly achieve and have dissimilar performance ratings to components. However, if your client is concerned about speech privacy, then that changes the answer a little bit. Somebody could literally walk up to the door and put their ear near or against the door, and now they're going to have the effect of that door panel at 45, and the fact that the wall is at 50 is of less consequence. So depending on the application and what it's being used for, the answer changes. But this is where an acoustic consultant or acoustic engineers can really help architects to determine what's best for their application, what meets their clients' needs the best. So I would recommend for um, you know, projects where you have a significant number of acoustic openings or where you have a significant requirement for acoustic abatement, that consulting with an architectural or an acoustic engineer is appropriate to help guide you through those types of questions.
Excellent. Thank you so much. Let's go ahead and end the poll now and share the results. So we have 23% always, 61% sometimes, and 17% never.
Okay. Well, it's an interesting result. I normally see the always a little higher and the never a little lower, but often the sometimes is the highest number. And I think that's probably right. There are applications, even though I think all acoustic door openings are tested as openings, there are applications where low performance acoustic performance is needed, but they're just looking for general sound abatement at a low level, and cost may be a defining factor. So that might be appropriate. But if if your client is looking for serious sound abatement, really the only way to know for sure what you're going to get is by using a tested and certified complete assembly, opening assembly, because that's the way it's tested in the lab. And bringing components together is going to be difficult and probably not produce the results that you desire. And we're going to talk about that a little more as we move along here. So, yeah, let's keep going. So, understanding the acoustic door. To begin with, it's important to realize that noise control indoors is particularly difficult to achieve because a door, unlike a wall or a floor, must be operable. Walls and floors have the luxury of achieving their acoustic goals in a typically 6 to 9 inch thick space, whereas architectural aesthetics and building functionality demand that an acoustic door will appear and function more as a normal 1 3/4 inch or thereabouts thick door. Acoustic assembly means that the assembly of the door leaf, single or paired door frame, the perimeter and bottom seals, thresholds, astragals at pairs, and acoustic glazing are to be supplied exactly as they were tested in an independent laboratory. Lab tested door and frame assembly should not be altered in the field. As demand for acoustic security becomes widespread in commercial and institutional construction, the standardized acoustic performance of door and frame assemblies, as well as acoustic board or side lights, has become essential. The current CSI standard specification, which is section 083474, requires the supply of an acoustic assembly when an acoustic opening is required. It is critical for operable door openings to be supplied as complete assemblies to ensure acoustic performance. Consequently, great care must be taken not only to specify laboratory tested door and frame assemblies, but also to ensure that these assemblies are installed in complete accordance with the manufacturer's instructions. Supplying openings as components is a recipe for problems in the field. And I really believe that if you're looking for acoustic results sort of above STC 40, you really should be considering a tested assembly. The other thing that I would say is, um, you could have the best product in the world, but if that product isn't installed correctly, it's also going to produce problems in the field. not only with acoustic performance, but potentially with functionality of the door opening. Acoustic steel door and frame assemblies combine outstanding sound transmission loss with the appearance of standard hollow metal products. They come complete with acoustic steel frames, perimeter and bottom seals, thresholds, and astragals at pairs that are all tested in accordance with ASTM E90 and E413 standards. Where vision lights are requested, the door will include a vision light kit, including glass factory installed based on the laboratory tested products. So it's not just what kind of glass is going into that opening, but how it gets installed in the door that helps the performance. Acoustic steel doors are 1 3/4 thick and are available from STC 33 to STC 53. They are also available in greater thicknesses from STC 54 to STC 59, and then engineered solutions are available for higher ratings. Lightweight panel engineering combined with level swing seal systems provide outstanding acoustic performance with easy operation. Additionally, cam lift hinges will be furnished for acoustic ratings above STC 46. Correctly installed openings can comply with ADA requirements, ANSI 117.1, without an operator through STC 51. Options include factory pre-installed acoustic glazing up to STC 55 and acoustic borrowed lights that can achieve up to STC 57. Fire labeled products have been tested in accordance with NFPA 80 and are supplied in singles or paired openings. So this chart provides the STC rating correlating with door specifications and other performance factors. In our slide deck, you will see, and I can provide a copy of this for your footnotes. But if we zoom in, you can see that the correlation of door STC rating, door thickness, and available area for glass. So as the STC rating changes, so do these measurements. So you have to really follow the data to understand what you can have for options and what's available at specific ratings. Acoustic wood door and steel frame assemblies provide the broadest range of sound transmission class or STC ratings in the industry, tested in accordance with E90 and E413. In an acoustic wood door and steel frame assembly, an acoustic steel core forms the substrate of the door leaf. So consequently, the hollow construction of wood-clad doors trap sound and perform at the STC levels of many steel doors. As a result, the building owner obtains the pleasing wood door aesthetic that is often preferred in the marketplace, combined with the rugged performance of a steel door. So if you consider the wood door construction, think a bit like more of a commodity fire rated door where they have a fire core, maybe it's mineral core, fiber materials, and then they have fire stop around the edge, intumescent, and either a hardwood or a veneered edge. And then they have a cross banded face veneer. Well, think of our acoustic wood door, similar construction, except instead of the fire core, you have an acoustic core, and you have a cross banded face veneer over top of the face and hardwood edges on the edge of the or perimeter of the door. So there may be more steel in that door than wood, but it looks and feels like a wood door. Acoustic wood door and steel frame assemblies are available in STC ratings up to and including STC 56. Doors are only 1 3/4 inches thick through STC 50, and greater thicknesses offer STC ratings from 51 to 56. Wood frames are available up to STC 45. Acoustic doors need not look any different from other specified commodity doors. The face veneers and matching door edges of acoustic wood door and steel frame assemblies are available in a variety of stain grade options that will match veneer choices on the rest of the project. The wood finishes of diverse manufacturers of wood doors and millwork can be matched with ease. I don't know about ease, but they can be matched readily. Stiles and rails are hardwood, and vertical edges match face veneers. Plastic laminate faces are also available, and those doors can be had with hardwood edges. So here's the same chart for wood doors. And again, if we zoom in on the chart, we can see where the door thickness and weight increases with the addition of fire ratings of 45 or 90 minutes. So as I explained, our acoustic wood door construction is basically, backward veneer over um, steel core with hardwood edges. Obviously, if we don't do some things differently, it would be very difficult to pass a fire test. So by default, we have to make that door a temperature rise door in order to pass the fire test. We have to control the rate at which the heat transfers through the door. We also have to protect the edge of that door, similar to what you do with a commodity door, with fire stop material and intumescents that are buried beneath the hardwood edges. So the fire rated wood door is a completely different construction than the non-fire rated wood door. A variety of accessories are available for acoustic assemblies. So accessories like hinges, both cam lift or heavyweight butt. So a cam lift hinge is generally used at higher ratings. We typically use it at STC 47 and higher. And what it does is lifts the door up as the door opens and drops it down on the bottom seal as it closes. So it does have a rise and fall of about quarter of an inch. So you do have to consider that with hardware. But it allows us to get both positive bottom seal, but also a little bit more tolerance around at the sill for installation. So that's really why cam lift hinges are preferred for higher ratings. They also carry more door weight than typical heavyweight butt hinges do. Astragals or mullions at pairs. Vision light kits, as I mentioned before, we would also include the glazing stops and the glass itself, and fire ratings or fire labels as well. So all of those would be considered accessories or options. It's advisable to consult with an acoustic expert if you are in a position to specify an STC rating for a door. In addition to consulting with an acoustic engineer, it is also important to consult with the specialty door and frame manufacturer. It is critical to ensure that the hardware and function of the opening are not in conflict with the acoustic attributes. And I really can't stress that enough. I will be happy to review hardware sets for acoustic openings to make sure that we've optimized the hardware choices to give you the function that you need, but also to give you the acoustic performance that you need. When an end user has a requirement for a given amount of sound reduction at a specific frequency, it is imperative to consult with a frame and door manufacturer and review their test data for compliance. So, for example, a mechanical room in a building may generate 80 decibels of sound at a frequency of 250 hertz. The requirement may be to reduce the noise at that frequency only by 40 decibels. So if one were to simply specify an acoustic door and frame of STC 40, it might not meet the owner's requirements. If you think back to that graph where I showed the STC contour, recall how it was a dashed line and it was lower at the lower frequencies than it was at the higher frequencies. So in the case of low frequency noise, if we just specify an average performance, we may not get the sound reduction needed at that low frequency itself. It is also imperative to consider the type of hardware that will be specified for each acoustic door opening to ensure proper function while not compromising acoustic performance. There really are far too many door configurations and hardware applications to list all of the do's and don'ts, not to mention access control and electronics. It is important for the architect or their hardware consultant to coordinate the best hardware applications for each acoustic openings. And these may be different from similar non-acoustic openings. So generally, one is simply required to source a product achieving a specific STC rating. Therefore, it is important that an STC rating is noted either on the remarks section of the door schedule or in section 083474 of the specification so that the acoustic performance requirement is clearly identified. Some manufacturers promote their acoustic doors by indicating that they have tested their door panels as inoperable panels. So while this is a legitimate approach to door panel development, it is obviously insufficient to ensure the acoustic performance of an operable acoustic door and frame assembly. So that's something to be looking for and why you want to ask for manufacturers' test data to make sure they've tested that product as an operable door assembly. As well, some manufacturers promote the use of acoustic seals, but have not tested them with a certified acoustic door and frame. The use of an entire tested assembly is crucial to the successful acoustic attenuation. Acoustic seals cannot simply be added to third-party door panels or door frames and achieve high-performance STC ratings. As portrayed in this table, non-acoustical doors paired with an acoustical component material such as seals do not produce worthwhile results, only adding maybe 2 to 3 levels to the final STC rating of a standard door. So unlike standard door assemblies, acoustic assemblies will greatly improve frame performance levels when paired with an acoustic component material such as seals. STC levels increase by more than 4 to 10 points with the use of proprietary seal systems independently tested as part of an STC assembly. Door panels should not be supplied in a door opening without tested perimeter seals and acoustic frames. Fully tested assemblies supplied by a single manufacturer should be specified, and a component approach should not be permitted. A variety of acoustic door assemblies are available to satisfy multiple design and performance criteria. So, for example, aesthetics, fire ratings, ADA requirements, and LEED. It is important to know that some manufacturers will modify their standard designs to meet the specific needs of a project. So, for example, if if your client wanted to use, I don't know, a concealed closer, well, the trade-off may be that in order to do that and maintain the acoustic rating, we have to substantially thicken the door so that the concealed closer can still be used and concealed within the door. The trade-off is time and cost. It's going to cost more for that solution, and it's going to take more time to produce it and manufacture it. So, it's not that it can't be done. The question is that something the client really wants to pay for? And I don't know the answer. I can only propose the solution. Most occupational environments require speech privacy. From boardrooms to patient exam rooms, the acoustic doors are critical or crucial to the acoustic plans. Enclosed rooms aren't a guarantee of complete acoustic separation unless dividing walls are designed as sound barriers. So, for instance, extending from the structural floor to the underside of the structural deck above, and continuous paths for sound are disrupted, sounds will pass through the partition. Openings in the partition must also be considered. Complete acoustic door assemblies instead of a separate door component are recommended. Both wood and steel door assemblies are fire tested in accordance with Underwriter Laboratories UL 10C standards. Wood door assemblies have been designed to achieve a 90-minute fire rating and an acoustic performance of up to STC 52. Steel door assemblies have been designed and tested to achieve 180-minute fire ratings and can meet an acoustic performance up to STC 56. Testing for these assemblies is conducted in accordance with UL10C UB7-2, NFPA 252, and ASTM E2964. A good place to look for guidance relating to acoustic designs in the office and a new construction setting is LEED. This is the preeminent program for the design, construction, maintenance, and operations of high-performance green buildings. The second of 3 goals under LEED for schools is contribute to occupant health. Specifically, health and human experience focuses on providing high-quality indoor environments that enhance productivity, decrease absenteeism, and improve the building's value. The USGBC has made acoustics a component of sustainable design by including it in the LEED v4, BD plus C, and ID plus C rating systems. Under the category Indoor Environment Quality, or EQ, the minimum acoustic performance prerequisite and the acoustic performance credit have applications for new construction, schools, hospitality, and healthcare under the BD plus C rating system, and for commercial interiors under the ID plus C rating system. So LEED v4 for schools environment quality prerequisite. So here the intent is to provide a classroom that are quiet so that teachers can speak to the class without straining their voices and students can effectively communicate with each other and the teacher. The requirements in background noise are to achieve a maximum background noise level 1 from heating, ventilating and air conditioning systems in classrooms and other core learning spaces of 40 dBA. LEED for schools EQ credit. So this is 1 to 2 points. And here the intent is to provide workspaces and classrooms that promote occupants' well-being, productivity, and communications through effective acoustic design. And the requirements for sound transmission are design classrooms and other core learning spaces to meet the STC requirements of ANSI S12.6. Requirements are for HVAC and background noise to achieve a background noise level of 35 dBA or less from HVAC systems in classrooms or core learning spaces. LEED v4 EQ credit for new construction and commercial interiors. Here the intent is to provide workspaces and training rooms that promote occupants' well-being, productivity, and communications through effective acoustical design. The requirements are for all occupied spaces to meet the following requirements as applicable to the space. So first is room noise levels, then sound isolation performance and constructions, limiting reverberation time and reverberant noise buildup, and finally paging, masking, and sound reinforcement systems. Projects that cannot meet sections of the requirements due to limited scope of work or historic preservation requirements must meet at least 3 of the above sections and then submit a detailed description justifying their design decisions. And finally, room noise levels. So mechanical noise is a particular challenge to control in a workplace environment due to the low frequency noise considerations. Also, HVAC air pressurization may affect door operation. And so that's important because we do find that can happen when we're sealing something 4 sides and you have negative pressure. So that's something to consider as well. Sound isolation. So when considering sound attenuation, all building components must be taken into account when designing areas where door, frame, and window assemblies are to be provided. Sound isolation criteria between various building areas must be carefully considered. This includes doors, frames, and windows where required. So this slide shows, and you should look for an acoustic door manufacturer that provides product-specific environmental product declarations, or EPDs, certified by ASTM International. So this particular manufacturer provides separate EPDs for wood doors, and steel frames. So if that's concern to your client, if they're looking for green solutions, this is an important feature. On request, wood door materials can meet other LEED credit rating criteria as well as Ford Stewardship Council or FSC standards. The acoustic assemblies utilize wood door panels where less than 10% of the product is obtained from the forest. The panels consist of laminated FSC or COC wood veneers with matching solid wood stiles and rails. Combined with an acoustic door core, these wood door products provide a post-consumer recycled content of well over 50%. Correctly installed acoustic door and frame assemblies may comply with handicap codes, specifically ANSI A117.1. Using lightweight door panels, level swing doors using butt hinges with sweep bottom seals, or cam lift hinges utilizing compression and sweep bottom seals are available to meet ADA compliance. When cam lift hinges are supplied, the closer arm must be designed to permit the lifting operation of the door panel. So that's approximately 1/4 of an inch. So you need to just make sure that you're using double arm, typically sort of avoid using track arm closers that have no flexibility in the arm. Acoustic door panels with superior STC ratings have been designed in standard 1 3/4 thicknesses, weighing between 7 pounds per square foot and 10 pounds per square foot. Custom door bottoms have been designed to complement these assemblies, enabling the use of heavyweight butt hinges. For STC 52 or higher ratings or larger door sizes, electric operators should be used for ADA compliance. So it's not just the STC rating that drives this, but also the door size can play a factor. We talked about HVAC and negative pressures. That can also play a factor. So there's sort of no hard and fast rule, but we can try to give you guidance. The other major factor that affects this is installation. The better the door is installed, the better compliance it's going to have with ADA. A SCIF is an accredited area where sensitive classified information may be handled, stored, and used, discussed, and/or processed. These areas are required by the U.S. Department of Defense and state where security and speech privacy are paramount. This is one location where acoustic specialty doors are definitely required. They must be an assembly. This type of a facility must be designed using the requirements of ICD and ICS 705. Along with requirements for perimeter walls, floors, and ceilings, there must only be one access to the facility, and the door itself has to be exacting requirements, including door material, thickness, and type. Rooms that require radio frequency shielding, security entry, and speech privacy would include similar specifications to a SCIF. So it is not uncommon for these types of security applications, both in government facilities, military facilities. We're also seeing this type of thing, the same spec being used for data centers, where they want to control acoustics as well as data. So they will have radio frequency protection alongside acoustic protection in a hybrid application. That brings us to the end of the presentation. So I would turn it over to you, Fulgence. Is there any questions?
Thank you so much, Steve. Yes, we did get a few questions, but I've included them in the Q&A report for you because we're a little bit out of time.
Gotcha. We're right on the clock.
Yes,
I
sir.
see that now. All right. Well, thank you very much, everyone, for your attention today. And I will take a look at any questions that Fulgence sends my way, and we'll get you answers to those out as soon as possible.
Thank you so much, Steve. Excellent presentation as always.
Thank you.
Thank you.
Bye.
All right, everyone, there is your session code. The final session code for today is 140052 140052. Please enter all your session codes at your ATS account dashboard at atsseminar.com. And it's also in the chat for you as well. Let me just send that one more time. There. 140052. There it is here. How can we reach Steve for support? I'm going to send that to you there. His contact info is going to be in the general chat, and I am responding to you right now, Carter. There is Steve's contact info there for you as well. All right. And with that said, if anyone needs any last minute credits, please visit the ATS On Demand course catalog at atsseminar.com. And shared this a little bit earlier, but we kindly encourage you to all please follow us on LinkedIn. And here is the QR code for you to join us on LinkedIn. We do have several weekly video updates on our LinkedIn, in addition to our new live stream podcast called Built for This. This Friday at 2:30 p.m. Eastern Standard Time, we'll be featuring Lisa Ayala. And the following week, we'll be featuring Trish Brindle with Fire Troll. So please join us on LinkedIn Live Friday at 2:30 p.m. Eastern Standard Time. And with that said, thank you for attending our seminar today. I'll stick around if you have any questions, but we hope you enjoy the rest of your day. And we'd love to have you back for another webcast soon. Peace, everyone. Hello, everyone. Fulgence here with ATS, and this week we're featuring a very popular on-demand course, Prefabricated Fireproof Columns, presented by Trish Brindle of Fire Troll. You'll get a quick look at the difference between active and passive fire protection, see how prefabricated fireproof columns stack up against other options, and pick up a few key design tips along the way. And here's something exciting. Trish will be joining Jen and I live right here on LinkedIn next week, Friday at 2:30 p.m. Eastern, for our next episode of Built for This, where we'll dive deeper into how Fire Troll's innovative fire-rated solutions are helping design professionals address compliance, performance, and aesthetics all at once. So check out the on-demand course now on atsseminar.com, and we'll see you live next week right here on LinkedIn.